Turn off the lights. Expand this window to full screen. Let the glow of distant galaxies fill your vision completely. What you're about to experience is not a quick summary, not a headline, not a digest. This is a full immersion into one of the most unsettling discoveries in the history of astronomy. A discovery so strange that it has forced cosmologists to question the very foundations of how we understand the universe's first moments. If you find yourself drawn to the mysteries that dwell at the edge of human knowledge, where our most refined instruments meet the boundaries of the comprehensible, consider subscribing. These documentaries are crafted for those who want to go deeper, far deeper, than the surface of science news. We don't skim. We descend. The universe is not what we thought. That sentence has been spoken before, countless times, often with exaggeration. But this time, the weight of evidence is different. The James Webb Space Telescope has turned its mirror toward the oldest light in the cosmos and found something that should not exist. Galaxies. Massive galaxies. Galaxies so large, so fully formed, so rich in stars, that according to every model we've built over decades of careful work, they are impossible. And yet, they are there. The silence after the Big Bang, the universe began in a state of unimaginable density and temperature approximately 13.8 billion years ago. In the first fraction of a second, the fundamental forces separated, particles condensed from energy, and the expanding fireball began its eternal cooling. This is not speculation. This is the model built from countless observations. The cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, the redshifts of distant objects. The Big Bang model has survived every major test for nearly a century. Within the first 3 minutes, the universe was still far too hot for atoms to exist. Protons and neutrons collided and fused into the lightest elements: hydrogen, helium, trace amounts of lithium. For the next 380,000 years, the universe remained opaque, a dense fog of plasma where photons could not travel freely. Every direction was bright with scattered light, a blinding glare with no shadows, no structure, no stars. Then, as expansion continued and temperatures dropped below 3,000 degrees Kelvin, electrons combined with nuclei to form neutral atoms. The photons decoupled from matter. The universe became transparent. The light from this moment is what we now observe as the cosmic microwave background, a faint, nearly uniform glow coming from every direction in the sky, cooled by expansion to just a few degrees above absolute zero. But transparency did not mean illumination. Once the primordial glow faded, the universe entered what cosmologists call the Dark Ages. There were no stars, no galaxies, no light sources except the fading afterglow of the Big Bang itself, redshifting into invisibility. For hundreds of millions of years, the cosmos was a vast, cold, dark expanse filled with hydrogen and helium gas, drifting under the influence of gravity. This was not a uniform darkness. The cosmic microwave background shows us tiny fluctuations in density, variations of only 1 part in 100,000. But those fluctuations were the seeds. Where the gas was even slightly denser, gravity pulled more material inward. Over time, these small overdensities grew, drawing in surrounding matter, collapsing slowly into the first structures. The Dark Ages lasted until gravity had concentrated enough gas into dense enough pockets that the pressure and temperature at the cores of these clouds triggered nuclear fusion. The first stars ignited. This moment, occurring somewhere between 100 million and 200 million years after the Big Bang, is called the cosmic dawn. It was the universe's first light since the primordial fireball, light born not from the cooling of the Big Bang, but from the furnaces of stellar cores. These first stars were unlike any stars that exist today. They formed from pristine gas, pure hydrogen and helium with no heavier elements, because no previous generation of stars had existed to create carbon, oxygen, iron. Without metals to help cool the gas clouds, these stars formed from much hotter, more massive collapsing regions. Theoretical models suggest the first stars were behemoths, perhaps 100 to 300 times the mass of our Sun, burning with extraordinary brilliance and dying quickly in spectacular supernovae after only a few million years. When these massive stars exploded, they scattered the first heavy elements into space. Subsequent generations of stars formed from gas enriched with these elements, allowing smaller, longer-lived stars to form. Over tens of millions of years, stars began to cluster. Gravity drew these clusters together. The first galaxies began to assemble. This is the narrative that has guided cosmology for decades. The first galaxies were expected to be small, dim, chaotic collections of stars, mere seeds that would grow over billions of years through mergers and accretion into the grand spiral and elliptical galaxies we see in the nearby universe today. The process was thought to be gradual, hierarchical, building from the bottom up, small structures forming first, then merging into larger ones, step by step, slowly assembling the cosmic architecture. The Hubble Space Telescope pushed our vision back to galaxies existing when the universe was only 500 million years old, and even further in a few exceptional cases. These early galaxies appeared small and irregular, consistent with expectations. They were the faint building blocks of the cosmos, scattered points of light in a still darkening sky. Then James Webb looked deeper. The aperture of revelation, the James Webb Space Telescope, is not simply a larger version of Hubble. It is an entirely different kind of instrument, designed with a singular purpose: to observe the universe in infrared light. This choice is not arbitrary. It is dictated by the nature of cosmic expansion itself. When light travels through expanding space, its wavelength stretches. A photon emitted as ultraviolet light from a galaxy in the early universe will, by the time it reaches us 13 billion years later, have been stretched into infrared. The further away an object is, the faster space expands between us and it, and the more the light is stretched, redshifted, toward longer wavelengths. The most distant galaxies, those formed in the first few hundred million years after the Big Bang, emit light that has been redshifted so dramatically that it becomes invisible to optical telescopes like Hubble. Their light now arrives as infrared radiation. James Webb's primary mirror is 6.5 meters across, composed of 18 hexagonal segments coated in gold to maximize infrared reflectivity. It sits not on Earth, but at the second Lagrange point, a gravitationally stable location 1.5 million kilometers from Earth in the direction opposite the Sun. Here, shielded from the heat of the Sun, Earth, and Moon by a 5-layer sun shield the size of a tennis court. The telescope operates at temperatures near 40 Kelvin, cold enough that its own thermal radiation does not overwhelm the faint infrared signals from the distant universe. The telescope carries 4 primary instruments. The near-infrared camera, NIR-CAM, is the primary imager, capable of detecting light from 0.6 to 5 microns in wavelength. The near-infrared spectrograph, NIR-SPEC, splits light into spectra, revealing the chemical composition, temperature, and motion of distant objects. The mid-infrared instrument, MIRI, extends observations to longer wavelengths up to 28 microns, probing cooler dust and more distant redshifted objects. The near-infrared imager and slitless spectrograph, NIRIS, provides wide-field imaging and spectroscopy, particularly useful for studying exoplanet atmospheres and faint distant galaxies. These instruments work in concert to achieve something unprecedented: the ability to observe galaxies at redshifts greater than 10, meaning galaxies whose light has been traveling for over 13 billion years, emitted when the universe was less than 500 million years old. Hubble could glimpse hints of this era, but James Webb can study it in detail. The telescope began science operations in the summer of 2022. Within weeks, the first deep-field images were released. The public saw beauty, a sparkling tapestry of galaxies stretching back through time. Astronomers saw something else. They saw objects that should not be there. Among the thousands of galaxies in the first deep images, researchers identified numerous candidates at extremely high redshifts of 10, 12, even higher. Spectroscopic follow-up confirmed many of these candidates. Galaxies existing at redshifts above 10 were not just detected. They were abundant, and they were not small. Photometric analysis, measuring the brightness of these galaxies across multiple infrared filters, allowed astronomers to estimate their stellar masses. The results were shocking. Some of these galaxies appeared to contain tens of billions of solar masses worth of stars. In some cases, the estimated stellar mass approached or even exceeded 100 billion solar masses, comparable to the mass of the Milky Way, a mature spiral galaxy in the present-day universe. But the Milky Way has had over 13 billion years to assemble its stars. These early galaxies had less than 500 million years. In cosmic terms, this is almost no time at all. The discovery triggered immediate debate. Some researchers questioned the photometric redshift estimates, suggesting the galaxies might be closer than they appeared, their light reddened by dust rather than cosmological expansion. Others questioned the stellar mass estimates, pointing to uncertainties in how we interpret the light from galaxies with unknown stellar populations and unknown chemical compositions. But as more data accumulated, as spectroscopic confirmations verified the distances, as independent teams reproduced the mass estimates using different methods, the pattern held. The galaxies were real. The distances were real. The masses were real. And the implications were profound. The problem of time to understand why these galaxies are considered impossible. One must understand the process of star formation, not as an abstract concept, but as a physical, time-dependent mechanism governed by the behavior of gas under gravity and the life cycle of stars themselves. Star formation begins with cold molecular gas. In the present-day universe, stars form in the densest regions of giant molecular clouds, where hydrogen molecules and dust grains shield the interior from radiation and allow the gas to cool to temperatures around 10 degrees Kelvin. When a region becomes dense enough and cold enough, gravity overcomes thermal pressure and the cloud collapses. As the collapsing gas heats up, nuclear fusion ignites and a star is born. This process is not instantaneous. The collapse of a molecular cloud core into a star takes time, typically hundreds of thousands to millions of years, depending on the mass of the forming star. Massive stars form faster, but are rarer. Low-mass stars form more slowly, but are far more numerous. The distribution of stellar masses that emerge from a collapsing cloud follows what is called the initial mass function, a statistical distribution heavily weighted toward low-mass stars. Once a star ignites, it enters the main sequence, fusing hydrogen into helium in its core. The duration of this phase depends on the star's mass. Massive stars burn through their fuel in a few million years. Solar mass stars burn for 10 billion years. Low-mass red dwarfs can burn for trillions of years, far longer than the current age of the universe. But here is the critical point. Building a galaxy of 100 billion solar masses requires converting gas into stars over an extended period. If we assume a typical initial mass function, most of those stars will be low-mass, long-lived objects. But those stars contribute little light. The luminosity of a galaxy is dominated by its massive stars, which are short-lived. To sustain a bright, massive galaxy, star formation must be continuous or at least prolonged over many generations of stellar life cycles. In the early universe, the situation is more complex. The gas is pristine, lacking the heavy elements that help cool molecular clouds in the present-day universe. Cooling is less efficient, which should make star formation less efficient. The first stars are expected to be extremely massive, burning brightly and dying quickly in supernovae. These explosions enrich the surrounding gas with metals, but they also inject energy into the gas, heating it and potentially blowing it out of the nascent galaxy, halting further star formation. This feedback, energy and momentum return to the interstellar medium by supernovae, stellar winds, and radiation from massive stars, is a crucial regulator of galaxy growth. Simulations show that in small early galaxies, feedback can be so strong that it expels most of the gas, effectively turning off star formation for extended periods. Only after the gas cools and falls back in can star formation resume. This cycle of bursts and quenching should slow the assembly of stellar mass, spreading galaxy growth over hundreds of millions or even billions of years. Moreover, galaxy growth is not just about turning gas into stars within a single object. It is also about mergers. Small galaxies collide and merge to form larger ones. Gas streams along filaments of dark matter, accreting onto galaxies and fueling new bursts of star formation. The hierarchical model of structure formation predicts that large galaxies assemble late, as the culmination of countless mergers of smaller systems. Given all these factors, the time required for star formation, the inefficiencies of early star formation in metal-poor gas, the disruption caused by feedback, the gradual buildup through mergers, cosmologists have calculated how massive a galaxy can plausibly become at any given time after the Big Bang. These calculations are based on models of structure formation rooted in our understanding of dark matter, dark energy, gravitational collapse, and gas dynamics. They have been tested and refined over decades, calibrated against observations of galaxies at various cosmic epochs. The consensus model predicts that by 500 million years after the Big Bang, the most massive galaxies should contain no more than a few billion solar masses and stars. Even this is pushing the boundaries, requiring highly efficient star formation and rapid assembly. Galaxies with tens of billions of solar masses should not appear until the universe is at least a billion years old. Galaxies approaching 100 billion solar masses, true giant galaxies, should not exist until several billion years after the Big Bang. Yet James Webb has found galaxies at redshifts of 10 to 13, corresponding to times between 400 and 300 million years after the Big Bang, with stellar mass estimates in the range of 10 billion to 100 billion solar masses. Some of the most extreme candidates, if confirmed, would contain stellar masses exceeding what the Milky Way possesses today, packed into a galaxy existing when a universe was less than 3% of its current age. This is not a minor discrepancy. This is not a small adjustment to the models. This is a chasm between observation and theory. The galaxies are too massive by factors of 10 or more. They contain too many stars, formed too quickly, in an era when the universe had barely begun to assemble its first structures. The language of redshift, understanding the depth of this problem, requires a precise understanding of redshift, the primary tool astronomers use to measure cosmic distances and look back in time. Redshift is defined as the fractional change in the wavelength of light due to the expansion of space. If a galaxy emits light at a wavelength of 500 nanometers and we observe it at 1,000 nanometers, the redshift is 1. The formula is straightforward. Redshift equals the observed wavelength minus the emitted wavelength, divided by the emitted wavelength. But redshift is not simply a measure of velocity, as it would be in the Doppler effect for objects moving through space. Cosmological redshift arises because space itself is expanding. As a photon travels through the universe, the fabric of space stretches, and the photon's wavelength stretches with it. The greater the distance the photon has traveled, the more space has expanded during its journey, and the higher the redshift. The relationship between redshift and time is not linear. It depends on the expansion history of a universe, which is governed by the relative densities of matter, dark energy, and radiation, as well as the curvature of space. In our universe, dominated by dark energy and matter, the relationship between redshift and cosmic age is calculated using the Friedmann equations derived from general relativity. A redshift of 0 corresponds to the present day. A redshift of 1 corresponds to a time when the universe was about 6 billion years old, roughly half its current age. A redshift of 2 corresponds to about 3 billion years after the Big Bang. As redshift increases, the corresponding cosmic age decreases rapidly. At redshift 6, the universe was less than 1 billion years old. At redshift 10, it was about 480 million years old. At redshift 13, it was approximately 320 million years old. James Webb has identified galaxies with spectroscopically confirmed redshifts above 10, and photometric candidates at redshifts as high as 16 or more. If the highest redshift candidates are confirmed, they would represent galaxies existing when a universe was only 250 million years old, barely past the end of the Dark Ages. These redshifts are not uncertain guesses. Photometric redshifts, estimated from the brightness of an object in multiple filters, can have significant uncertainties, especially at extreme distances. But spectroscopic redshifts, measured from the precise wavelengths of emission and absorption lines in a galaxy's spectrum, are highly reliable. They provide a direct measurement of how much the light has been stretched by cosmic expansion, and thus a precise determination of when the light was emitted. Several of the most massive early galaxy candidates, discovered by James Webb, have been followed up with spectroscopy using the NIR SPEC instrument. The spectra show clear emission lines, hydrogen, oxygen, and other elements, shifted to longer wavelengths by factors of 10 or more. The redshifts are unambiguous. The galaxies are genuinely ancient, and this makes the mass estimates all the more troubling. Weighing ghosts measuring the mass of a galaxy 13 billion light-years away is not straightforward. We cannot simply count the stars. We must infer the stellar mass from the light we receive, using our understanding of how stars of different types emit light across the electromagnetic spectrum. The process begins with photometry. Telescopes measure the brightness of a galaxy in multiple filters, each sensitive to a different range of wavelengths. For James Webb, this means filters spanning the near and mid-infrared from roughly 1 to 28 microns. By comparing the brightness in different filters, astronomers construct a spectral energy distribution, a graph showing how much light the galaxy emits at each wavelength. This spectral energy distribution contains information about the galaxy's stellar population. Young, hot, massive stars emit most of their light at short wavelengths, ultraviolet and blue. Old, cool, low-mass stars emit most of their light at long wavelengths, red and infrared. Dust absorbs short wavelength light and re-emits it at longer wavelengths, complicating the picture. The overall shape of the spectral energy distribution reflects the mix of stellar ages, masses, and the amount of dust present. To extract a stellar mass estimate, astronomers compare the observed spectral energy distribution to models. These models, called stellar population synthesis models, simulate the light emitted by a galaxy with a given star formation history, initial mass function, chemical composition, and dust content. By finding the model that best matches the observed data, astronomers can estimate the total stellar mass. This method has been used successfully for decades on nearby galaxies, where it can be tested against other mass measurement techniques, such as dynamical masses derived from the motion of stars and gas. The agreement is generally good, giving confidence that stellar population synthesis provides reliable mass estimates. But for the earliest galaxies, uncertainties multiply. The stellar populations in these galaxies are unlike anything in the nearby universe. They are forming stars from gas with very low metallicity, few heavy elements, because previous generations of stars have had little time to enrich the interstellar medium. The initial mass function might be different, perhaps weighted more heavily toward massive stars. The star formation history is unknown. Did these galaxies form their stars in a single intense burst, or over multiple episodes? Dust properties in the early universe might differ from those today. Each of these uncertainties affects the inferred stellar mass. If the initial mass function is top-heavy, with more massive stars than usual, the galaxy could be more luminous for a given stellar mass, leading to an overestimate. If dust is reddening the light, it could be mistaken for an older stellar population, again leading to an overestimate. Some critics of the early massive galaxy findings have argued that these uncertainties could account for the discrepancy, that the galaxies might be less massive than they appear if we are misinterpreting their light. But multiple independent studies have tested these possibilities. Researchers have explored models with varying initial mass functions, different star formation histories, extreme dust properties. While these variations change the estimated stellar mass, they do not eliminate the problem. Even under the most conservative assumptions, Many of these galaxies still have stellar masses of several billion to tens of billions of solar masses. The most extreme objects might be somewhat less massive than initial estimates, but they remain far more massive than theoretical predictions allow. Moreover, spectroscopy provides additional constraints. Emission lines from ionized gas reveal the presence of heavy elements like oxygen, indicating that star formation has been ongoing long enough to enrich the interstellar medium. The strength of these lines can be used to estimate star formation rates, which are often found to be very high, hundreds to thousands of solar masses per year. Such high rates, sustained over even a few tens of millions of years, would build up enormous stellar masses very quickly. Dynamical mass measurements, though more challenging at these distances, are beginning to be attempted using observations of gas kinematics. The rotation speed and velocity dispersion of gas within a galaxy reflect the gravitational potential, and thus the total mass, stars, gas, and dark matter combined. Early results suggest that the total masses of these galaxies are indeed very high, consistent with the large stellar masses inferred from their light. The evidence from multiple independent lines of reasoning converges on the same conclusion. These galaxies contain far more stars than they should. They have assembled stellar masses in a few 100 million years that should require 1 billion years or more. They defy the standard model of galaxy formation. The dark scaffold. To appreciate the full scope of the problem, one must consider the role of dark matter. Galaxies do not form in isolation. They form within dark matter halos, vast, invisible structures made of particles that interact only through gravity, not through electromagnetism, and thus emit no light. Dark matter constitutes about 85% of the total matter in the universe. It does not clump as tightly as ordinary matter because it cannot dissipate energy through radiation. Instead, it forms extended halos within which ordinary matter, gas, falls and collects. The gas, unlike dark matter, can cool by radiating energy, allowing it to condense into dense clouds where stars form. The galaxy we see is the luminous tip of a much larger dark matter structure. The mass of a dark matter halo determines how much gas it can hold and, consequently, how massive a galaxy can grow within it. In the standard cosmological model, known as lambda cold dark matter, the growth of dark matter halos is well understood. Structure forms hierarchically. Small halos collapse first, then merge to form larger halos over time. By tracking the growth of halos as a function of time, cosmologists can predict the maximum halo mass at any given redshift. The relationship between halo mass and stellar mass is not one-to-one. Only a fraction of the gas in a halo turns into stars. The rest remains as diffuse gas or is expelled by feedback. The stellar-to-halo mass ratio depends on the efficiency of star formation and the strength of feedback processes. Observations of galaxies at low redshift have established this relationship empirically, showing that the most efficient star formation occurs in halos of a particular mass, around 10 to the 12 solar masses. In smaller halos, supernova feedback is very effective at expelling gas. In larger halos, gas heating by gravitational shocks and feedback from supermassive black holes suppresses star formation. As a result, the stellar-to-halo mass ratio peaks at a few percent and declines for both lower and higher halo masses. Applying this framework to the early universe, we can ask, what is the maximum stellar mass a galaxy could have at redshift 10? The answer depends on the maximum halo mass available at that time. Simulations of structure formation in the lambda cold dark matter model predict that the most massive halos at redshift 10 have masses around 10 to the 11th to 10 to the 12th solar masses. Assuming a stellar-to-halo mass ratio of a few percent, the maximum stellar mass should be a few billion solar masses at most. Yet the observed galaxies have stellar masses of 10 billion solar masses or more, exceeding the predicted maximum by factors of 5 to 10 or greater. This is not a matter of slightly more efficient star formation. To fit these observations into the standard model would require stellar-to-halo mass ratios of 50% or higher, meaning that half of all the gas in the halo has been turned into stars. This is far beyond what is observed at any epoch in the universe's history. It would require star formation to be extraordinarily efficient and feedback to be almost entirely absent, both of which contradict our understanding of the physical processes involved. Some researchers have explored the possibility that the halos themselves are more massive than the standard model predicts. Perhaps the initial conditions of the universe, the density fluctuations imprinted at the end of inflation, had a different statistical distribution than assumed, with more power on small scales, allowing denser, more massive structures to form earlier. But this would require modifications to the inflationary model or the properties of dark matter itself, changes that would have far-reaching consequences for many other observations, including the cosmic microwave background and the large-scale structure of the universe. Such modifications are possible, but they cannot be made lightly. They must be consistent with all other cosmological data, and at present, no proposed modification achieves this without creating new problems elsewhere. Another possibility involves the nature of dark matter. The standard assumption is that dark matter is cold, meaning the particles have low velocities and can clump on small scales. If dark matter were warm, with higher particle velocities, it would erase structure on small scales, delaying the formation of the first halos. This would make the problem worse, not better. Alternatively, if dark matter has interactions beyond gravity, if it can self-interact or interact with ordinary matter in subtle ways, this could alter the halo mass function. But again, such modifications are tightly constrained by other observations. The dark matter scaffold, as predicted by the standard model, simply does not support the construction of such massive galaxies so early. The foundation is too small, the building too large, the time too short. The engines of creation, even if dark matter halos were massive enough, the question remains: how do you turn gas into stars fast enough to build a galaxy of 100 billion solar masses in 300 million years? Star formation in the present-day universe is a slow, inefficient process. Observations of nearby star-forming galaxies show that they convert only a small fraction of their gas into stars per unit time. The star formation rate is typically proportional to the gas mass, with a proportionality constant, the star formation efficiency, of about 1% per million years. This means it takes roughly 100 million years to convert 1% of the gas into stars. At this rate, building a galaxy with 100 billion solar masses would require a gas reservoir of 10 trillion solar masses sustained over 10 billion years, or a smaller gas reservoir replenished continuously by accretion from the intergalactic medium. In the early universe, conditions are different. The gas is collapsing into halos for the first time, compressed by gravity, potentially forming stars at higher rates. But there are also factors that reduce efficiency. The gas is hotter, turbulent, and prone to being blown out by supernova feedback. The first generations of stars are massive and short-lived, exploding before subsequent generations can form, injecting energy that heats the surrounding gas and can halt star formation entirely. To achieve the observed stellar masses, star formation in these early galaxies must be extraordinarily rapid. Estimates suggest star formation rates of hundreds to over 1,000 solar masses per year would be needed, sustained over 100 to 200 million years. While high star formation rates have been observed in some extreme starburst galaxies in the present-day universe, such bursts are usually brief, triggered by galaxy mergers or other transient events, and they consume the available gas quickly. Sustaining such rates for hundreds of millions of years requires a continuous supply of gas. Where does this gas come from? In the hierarchical model, gas accretes onto galaxies along cosmic filaments, streams of matter funneling into the gravitational wells of dark matter halos. This process, called cold mode accretion, can supply gas at high rates in the early universe, when a universe is denser and halos are growing rapidly. Simulations show that cold streams can penetrate deep into halos, delivering gas directly to the central galaxy without being shock-heated, allowing efficient star formation. But even cold mode accretion has limits. The rate at which gas can be supplied depends on the halo mass and the surrounding environment. For a halo of 10 to the 12 solar masses at redshift 10, simulations predict gas accretion rates of tens to perhaps 100 solar masses per year. This is sufficient to fuel vigorous star formation, but it is still marginal for building the most massive galaxies observed by James Webb. And this assumes that all the accreting gas turns into stars, with no losses to feedback, an assumption that is almost certainly wrong. Furthermore, rapid star formation generates copious amounts of radiation. Young, massive stars emit intense ultraviolet light, ionizing the surrounding gas. This ionization heats the gas to thousands of degrees, increasing its thermal pressure and making it harder for gravity to compress it into new stars. The radiation also exerts pressure on dust grains, driving winds that can expel gas from the galaxy. Supernovae inject even more energy, both thermal and kinetic, creating hot bubbles that expand and blow out into the intergalactic medium. This feedback is observed in nearby starburst galaxies, where powerful outflows of gas are driven by the collective effect of many supernovae. In small, early galaxies, the gravitational potential is shallow. It doesn't take much energy to unbind gas and expel it from the galaxy entirely. Once the gas is gone, star formation stops. The galaxy must wait for the gas to cool and fall back in, or for new gas to be accreted from the surroundings. This cycle of star formation, feedback, quenching, and reignition should limit the rate at which stellar mass accumulates. Yet the observed galaxies show no signs of such limitations. They are massive, luminous, apparently forming stars at prodigious rates without being disrupted. It is as if feedback, one of the most important regulatory mechanisms in galaxy evolution, is somehow ineffective or absent. But we have no physical reason to believe feedback would be weaker in the early universe. If anything, it should be stronger because the galaxies are smaller and the star formation is more concentrated. This is the engine problem. We do not understand how these galaxies generate stars so quickly, so efficiently, in the face of processes that should slow them down. The engines of creation are running far faster than the laws of physics, as we understand them, should allow. The paradox of maturity, the massive early galaxies discovered by James Webb, are not only too massive, they are too mature. Their light, analyzed in detail through spectroscopy, reveals properties that suggest they are not freshly formed systems, but galaxies that have already undergone significant evolution. Maturity in a galaxy is indicated by several observational signatures. One is the presence of old stars. Young stellar populations emit most of their light at short wavelengths, blue and ultraviolet, because they contain massive, hot stars. Old stellar populations, dominated by low-mass stars that burn slowly, emit most of their light at long wavelengths, red and near-infrared. A galaxy whose light is dominated by red colors is likely to contain a large population of old stars. Several of the massive galaxies at redshift 10 to 13 observed by James Webb show spectral energy distributions that are surprisingly red. Their light peaks at wavelengths longer than expected for a galaxy undergoing vigorous star formation. This redness suggests that a significant fraction of their stellar mass is in stars that formed at even earlier times and have since aged. In other words, these galaxies contain stars that must have formed at redshifts of 15 or higher, corresponding to times less than 300 million years after the Big Bang, pushing back the problem even further. Another indicator of maturity is metallicity, the abundance of elements heavier than hydrogen and helium. In the early universe, gas is initially pristine, containing only the elements forged in the Big Bang. Stars synthesize heavier elements in their cores and release them into the interstellar medium when they die, either gradually through stellar winds or explosively in supernovae. Over successive generations of star formation, the metallicity of the gas increases. A high metallicity indicates that many generations of stars have lived and died, enriching the gas over an extended period. Spectroscopic observations of some massive early galaxies reveal emission lines from oxygen, nitrogen, and carbon. The strength of these lines, relative to hydrogen, allows astronomers to estimate the gas phase metallicity. Surprisingly, some of these galaxies have metallicities that are not negligible. They are a significant fraction of solar metallicity, far higher than expected for galaxies only a few 100 million years old. This implies that chemical enrichment has proceeded very rapidly, requiring multiple generations of star formation and stellar death in a very short time. Yet another sign of maturity is structure. In the present-day universe, galaxies come in a variety of morphologies: spirals with ordered disks and spiral arms, ellipticals with smooth, featureless distributions of stars, irregulars with chaotic, asymmetric structures. The morphology of a galaxy reflects its formation history. Spirals are thought to form through the gradual accretion of gas and the settling of that gas into a rotating disk. Ellipticals are thought to form through violent mergers of smaller galaxies, which destroy disks and create a dispersion-supported stellar distribution. Irregular galaxies are often young, still in the process of assembling. The first galaxies were expected to be irregular, small, clumpy, chaotic systems without clear structure because they had not yet had time to settle into organized configurations. But high-resolution imaging of some massive early galaxies with James Webb reveals that they are not uniformly chaotic. Some show evidence of central concentration, suggesting the formation of dense cores or even protobulges. Some show hints of extended structures or multiple clumps that might represent merging components. A few even show indications of disk-like morphology, though interpreting structure at such distances is challenging. The presence of any significant structure is puzzling. Structure formation takes time. A rotating disk forms as gas loses angular momentum and spirals inward, a process mediated by gravitational torques and turbulence. A spheroidal bulge forms through dynamical processes, mergers, violent relaxation, secular evolution, that redistribute stellar orbits. These processes are not instantaneous. They require many dynamical times, where a dynamical time is the time it takes for a star to orbit through the galaxy. For a galaxy of a given size, the dynamical time is proportional to the square root of the size divided by the gravitational acceleration. For early galaxies compact and dense, dynamical times are relatively short, perhaps 10 to 100 million years. But even so, significant structural evolution requires multiple dynamical times. The combination of high stellar mass, red colors indicating old stellar populations, elevated metallicity, and emergent structure paints a picture of galaxies that have undergone a full cycle of evolution in a time interval that seems impossibly brief. It is as if we are observing galaxies that should be 1 billion years old, but we are seeing them when the universe is only 300 million years old. The paradox is not just that they exist, but that they appear so mature, so evolved, so finished. The spectroscopic confirmation cascade, as the first James Webb deep images revealed candidate high redshift galaxies, the astronomical community reacted with a mixture of excitement and skepticism. Photometric redshifts, based on broadband colors, can be misleading. Objects reddened by dust, or with unusual spectral properties, can masquerade as extremely distant galaxies. History is filled with examples of claimed high redshift galaxies that, upon closer inspection with spectroscopy, turn out to be much closer, their colors mimicking the signature of distance. Spectroscopy is the gold standard. By dispersing the light of an object into a spectrum, revealing the precise wavelengths of emission and absorption lines, astronomers can measure the redshift directly and unambiguously. If a galaxy emits a hydrogen emission line at a rest wavelength of 121 nanometers and a line is observed at 1,331 nanometers, the redshift is exactly 10. There is no ambiguity, no room for misinterpretation. The NIR SPEC instrument on James Webb is designed for this purpose. It is a multi-object spectrograph capable of observing dozens of objects simultaneously using configurable microshutters that block light from unwanted regions of the sky while allowing light from targets to pass through. This makes it possible to obtain spectra of many high redshift galaxy candidates in a single observation, efficiently following up the photometric discoveries. In the months following the release of the first deep images, spectroscopic campaigns were initiated. Teams of astronomers targeted the most promising candidates, galaxies with photometric redshifts above 10, to confirm their distances and study their properties in detail. The results were startling. Many of the candidates were confirmed. Their spectra showed clear emission lines, hydrogen Lyman alpha, hydrogen Balmer lines, oxygen doublets, shifted to wavelengths consistent with redshifts between 10 and 13. The confirmations eliminated the possibility that these objects were nearby imposters. They were genuinely at the distances inferred from their colors. They were genuinely ancient. But the spectra also revealed unexpected features. Some galaxies showed very strong emission lines, indicating intense ionization of the gas by massive stars or perhaps active galactic nuclei. Others showed evidence of outflows, with emission lines broadened or blue shifted, indicating gas being expelled from the galaxy at velocities of hundreds of kilometers per second. Still others showed absorption features indicative of mature stellar populations, reinforcing the impression that these were not newborn galaxies, but systems that had already undergone substantial evolution. One particularly striking case involved a galaxy at a spectroscopically confirmed redshift of approximately 13. The galaxy was initially identified as a photometric candidate and appeared extremely red. Spectroscopy confirmed its redshift and revealed a spectrum dominated by emission from oxygen and hydrogen, with very little ultraviolet continuum light. The lack of ultraviolet light suggested that the galaxy's star formation might have recently ceased, allowing the massive short-lived stars to die off, leaving behind a population of longer-lived, redder stars. If true, this would imply a galaxy that formed its stars even earlier, underwent a burst of star formation, and then quenched, all within the first few 100 million years after the Big Bang. The timeline becomes not just tight, but absurdly compressed. Another confirmed galaxy at redshift 12 exhibited a high star formation rate, estimated from the strength of its emission lines to be over 1,000 solar masses per year. Sustaining such a rate for even 50 million years would produce 50 billion solar masses of stars. Yet the galaxy was observed at a time when the universe was only 370 million years old, leaving barely enough time for even one such burst, let alone the multiple episodes that would be needed to explain the galaxy's inferred stellar mass and chemical enrichment. As confirmations accumulated, the initial skepticism began to shift. These were not flukes. They were not misidentified objects. They were real galaxies at real distances with real masses. The universe at redshift 10 and beyond was not the sparse, dim, infant universe anticipated by theory. It was populated with massive, luminous, actively star-forming galaxies that had no right to exist. The crisis in lambda cold dark matter, the standard cosmological model, lambda cold dark matter, is one of the most successful scientific theories ever developed. It explains the large-scale structure of the universe, the cosmic microwave background radiation, the abundance of light elements, the accelerated expansion of the universe, and the distribution of galaxies across cosmic time. It has been tested and refined over decades, with parameters measured to exquisite precision by experiments such as the Planck satellite. But the model is not without tensions. Even before James Webb, there were indications that something might be amiss. One such tension is the Hubble constant problem. The Hubble constant measures the current rate of expansion of the universe. Measurements based on the cosmic microwave background, assuming the lambda cold dark matter model, predict a Hubble constant of about 67 kilometers per second per megaparsec. But measurements based on observations of nearby, supernovae, and Cepheid variable stars yield a higher value, around 73. The discrepancy is statistically significant and has persisted despite numerous efforts to identify systematic errors in either method. If real, it suggests that either our cosmological model is incomplete or our understanding of stellar evolution and supernova physics is flawed. Another tension involves the amplitude of structure in the universe. Measurements of the cosmic microwave background predict a certain level of clumpiness in the distribution of matter on large scales. But observations of gravitational lensing and galaxy clustering suggest that the universe is slightly less clumpy than expected. This discrepancy, known as the S8 tension, is less severe than the Hubble tension, but it hints at possible issues with the growth of structure. The discovery of massive galaxies at high redshift adds a new tension, perhaps the most severe yet. These galaxies imply that structure formation in the early universe proceeded much faster than the model predicts. Dark matter halos collapsed earlier, gas cooled and formed stars more efficiently, and galaxies assembled more quickly. To accommodate these observations within the lambda cold dark matter framework would require significant adjustments to the parameters or the physics of galaxy formation. One possible adjustment is to increase the amplitude of primordial density fluctuations on small scales. If the initial seeds of structure were denser in localized regions, those regions could collapse earlier and form more massive halos sooner. But this would affect not only high redshift galaxies, but also the entire structure of the universe. It would lead to more small-scale structure everywhere, which is not observed. It would also alter the predictions for the cosmic microwave background in ways that are inconsistent with Planck's measurements. Another possibility is to modify the properties of dark matter. If dark matter particles could interact with each other or with ordinary matter in ways not currently included in the model, this could affect the rate at which halos collapse and galaxies form. For instance, if dark matter could lose energy through some form of interaction, it could collapse into denser configurations more quickly. But such interactions are tightly constrained by a host of other observations, including the shapes of dark matter halos, the behavior of dark matter in galaxy clusters, and the cosmic microwave background. A more radical possibility is to revisit the assumption that dark matter is cold. If dark matter is warm, with particles moving at higher speeds, this suppresses structure formation on small scales and delays the formation of the first galaxies, making the problem worse. But if dark matter has a more complex nature, perhaps consisting of multiple particle species with different properties, this could alter the timeline of structure formation in nuanced ways. However, no specific model of this type has yet been proposed that solves the massive galaxy problem without conflicting with other observations. Some researchers have proposed modifications to the expansion history of the universe. If the expansion rate was different in the early universe than the standard model assumes, this would change the relationship between redshift and cosmic time, potentially giving galaxies more time to form. But the expansion history is tightly constrained by multiple independent observations, including the cosmic microwave background, baryon acoustic oscillations, and supernova distances. Any modification must fit all of these data, and none proposed so far succeeds. There is also the possibility that the problem lies not with cosmology, but with our understanding of baryonic physics, the processes involving ordinary matter. Perhaps star formation in the early universe was far more efficient than current models assume. Perhaps feedback was weaker, allowing gas to remain in galaxies and continue forming stars. Perhaps the initial mass function was different, producing more light per unit stellar mass and leading to overestimated masses. These are plausible explanations, but they require invoking processes that are not observed in any other context and for which we have no theoretical justification. The lambda cold dark matter model is under strain. It is not broken. Most of its predictions remain consistent with observations. But the discovery of massive early galaxies is a crack in the foundation, a piece of evidence that does not fit comfortably within the existing framework. Whether this crack can be patched with adjustments to astrophysical processes or whether it signals the need for a deeper revision of cosmological theory remains an open question. The alternative explanations, dust and deception, when confronted with observations that challenge fundamental theory, scientists must carefully consider whether the observations themselves might be misinterpreted. In the case of the massive early galaxies, the primary concern is whether the photometric redshifts and stellar mass estimates are accurate. Could these galaxies be closer than they appear? Could their masses be overestimated? One potential source of error is dust. Interstellar dust consists of tiny, solid grains, mostly silicates and carbonaceous materials, that absorb and scatter light. Dust is particularly effective at absorbing short-wavelength ultraviolet and blue light, while allowing longer-wavelength red and infrared light to pass through. When a galaxy contains dust, its light becomes reddened, shifted toward longer wavelengths, mimicking the effect of cosmological redshift. A dusty galaxy at low redshift could, in principle, have colors similar to a dust-free galaxy at high redshift. Photometric redshift estimates, which rely on matching observed colors to model templates, could be fooled. If this were the case, the apparently distant massive galaxies might actually be relatively nearby dusty galaxies, and the entire problem would evaporate. To test this possibility, astronomers look for other indicators of distance. Dust reddening affects all wavelengths, but in a predictable way. It creates a smooth, featureless change in the spectral shape. Cosmological redshift, on the other hand, shifts specific spectral features, emission and absorption lines, to new wavelengths while preserving their spacing. Spectroscopy can distinguish between the two. If a galaxy's spectrum shows emission lines at wavelengths consistent with high redshift, it is truly distant, not merely dusty. As discussed, many of the massive galaxy candidates have now been confirmed spectroscopically. Their redshifts are genuine. Dust reddening cannot explain their colors. They are at the distances initially inferred from photometry. But even for spectroscopically confirmed high redshift galaxies, dust can still affect mass estimates. If a galaxy contains significant dust, the dust absorbs some of the ultraviolet and optical light emitted by stars and re-emits it at longer wavelengths in the infrared. This makes the galaxy appear dimmer in the ultraviolet and brighter in the infrared than it would be in the absence of dust. When fitting stellar population models to the observed spectral energy distribution, the presence of dust must be accounted for. If the dust content is underestimated, the model might overestimate the stellar mass to compensate for the observed infrared brightness. However, dust also has a distinct spectral signature. It produces a broad emission feature at mid-infrared wavelengths, and its emission has a characteristic shape determined by the temperature of the dust grains. The MIRI instrument on James Webb, sensitive to mid-infrared light, can detect this emission. Observations so far have not shown the extreme levels of dust emission that would be required to explain the brightness of the massive early galaxies as predominantly dust-reprocessed starlight. The galaxies are intrinsically luminous in the infrared because they contain large populations of red stars, not because they are heavily dust-enshrouded. Furthermore, detailed modeling efforts have explored a range of dust properties and quantities. Even when allowing for maximal plausible dust content, the inferred stellar masses remain very high, often reduced by only a factor of 2 or 3, not the factor of 10 or more that would be needed to reconcile observations with theory. Dust can introduce uncertainty, but does not resolve the discrepancy. Another possible source of error is the stellar population models themselves. These models rely on our understanding of stellar evolution, stellar atmospheres, and the initial mass function. If stars in the early universe had different properties than those observed today, the models might systematically misinterpret the light from early galaxies. For example, if the initial mass function in the early universe were top-heavy, weighted toward more massive stars, then for a given stellar mass, the galaxy would be more luminous because massive stars are much brighter than low-mass stars. This would mean that photometric measurements would overestimate the stellar mass. The galaxy is bright not because it contains many stars, but because the stars it contains are individually very luminous. This is a legitimate concern, and researchers have investigated it extensively. Models with top-heavy initial mass functions have been applied to the James Webb data. The result is that the inferred stellar masses decrease, but not by enough. Even with extreme assumptions, initial mass functions so top-heavy that they border on the physically implausible, the stellar masses remain in the range of several billion to tens of billions of solar masses, still far exceeding theoretical predictions. Moreover, a top-heavy initial mass function has other consequences. Massive stars produce copious amounts of ionizing radiation and die in supernovae, enriching the interstellar medium with heavy elements. If the initial mass function were top-heavy, we would expect very high ionizing photon outputs and rapid chemical enrichment. While some early galaxies do show high ionizing photon production, the levels are not extreme enough to require dramatically top-heavy initial mass functions. And the observed metallicities, while elevated, are not so high as to demand an overabundance of massive stars. Another consideration is the possibility of active galactic nuclei, supermassive black holes accreting gas and emitting intense radiation. An active galactic nucleus can be extraordinarily luminous, potentially outshining the entire stellar population of its host galaxy. If a significant fraction of the light from these early galaxies comes from an active galactic nucleus rather than stars, the stellar mass estimates would be too high. Spectroscopy again provides a diagnostic. Active galactic nuclei have characteristic emission line ratios, strong, broad lines from highly ionized species such as ionized oxygen, neon, and iron. Stellar populations produce different line ratios, dominated by narrower lines from less extreme ionization states. By examining the emission line spectra of the massive early galaxies, astronomers can assess the contribution from active galactic nuclei. Some of the early galaxies do show signs of active galactic nuclei, but not all. And even in cases where an active nucleus is present, it typically does not dominate the total light. The stellar populations are still inferred to be very massive. Moreover, the presence of an active nucleus introduces its own puzzle. Supermassive black holes themselves take time to grow. Finding million or billion solar mass black holes in galaxies only a few hundred million years old is another challenge for theory, compounding rather than resolving the problem. Alternative explanations involving observational errors or misinterpretations have been explored thoroughly. They can account for some of the uncertainty, and they may reduce the estimated masses of the most extreme objects somewhat, but they do not eliminate the fundamental discrepancy. The massive early galaxies are real. Their masses, while uncertain, are robustly inferred to be far higher than theoretical predictions allow. The first billion years, a recalibrated history, the discovery of massive galaxies at redshifts 10 to 13 forces a recalibration of our narrative of the universe's first billion years. The timeline we have told for decades, based on careful theoretical modeling and observational hints from Hubble and ground-based telescopes, must now be revised. Let's walk through this first billion years again, but now informed by what James Webb has revealed. The universe begins. Inflation imprints quantum fluctuations as density variations across space. The fireball cools. Nucleosynthesis creates hydrogen and helium. Recombination makes the universe transparent. The cosmic microwave background photons begin their journey to us, carrying the imprint of these tiny density fluctuations. The dark ages begin, but they may be shorter than we thought. The density fluctuations grow under gravity. Dark matter halos begin to collapse, pulling in gas. The first stars ignite, perhaps at redshift 30 or higher, within 100 million years of the Big Bang, or even sooner. These first stars are massive, luminous, and brief. They explode, enriching their surroundings with the first heavy elements, but also possibly seeding the formation of the first black holes, some of which may grow rapidly by accreting gas from dense environments. By redshift 20, perhaps 150 million years after the Big Bang, the first small galaxies have assembled. But small may be a relative term. Already, these proto-galaxies might contain millions of solar masses and stars, formed in intense bursts, their light ionizing bubbles of hydrogen around them, beginning the reionization of the universe. By redshift 15, 250 million years after the Big Bang, galaxies are abundant. They are merging, colliding, exchanging gas. Star formation is widespread, perhaps more widespread than theory predicted. The gas cooling and collapsing into these galaxies is not being disrupted as efficiently by feedback as models assumed. Perhaps the geometry of gas accretion, cold streams penetrating deep into halos, shields the gas from the energy injected by supernovae, allowing star formation to continue unabated. By redshift 13, 320 million years after the Big Bang, some galaxies have already assembled tens of billions of solar masses and stars. They are not scattered rarities, but a noticeable fraction of the galaxy population. Their light is redshifted into the infrared, invisible to Hubble, but blazing in the view of James Webb. They contain old stars, indicating that their star formation began even earlier. They have already enriched their gas with heavy elements, indicating multiple generations of stellar evolution. They have structure, central concentrations, possibly even the beginnings of disks or bulges. By redshift 10, 480 million years after the Big Bang, the universe is teeming with galaxies. Some are small and irregular, as expected, but a significant number are massive, mature, organized. The cosmic star formation rate density, the total rate of star formation per unit volume of the universe, is higher than previously believed. The reionization of hydrogen, the process by which ionizing radiation from stars and galaxies breaks apart the neutral hydrogen atoms filling intergalactic space, may be proceeding faster, driven by this unexpectedly vigorous population of early galaxies. By 1 billion years, redshift 6, the picture is more familiar. Large galaxies have assembled through mergers and accretion. The Hubble Space Telescope observed this epoch extensively, finding galaxies that match theoretical expectations. But the foundation on which these galaxies are built is now understood to be different. They did not grow slowly from tiny seeds. They grew rapidly from seeds that were already large, already massive, already evolved. The revised history suggests a universe that wasted no time, that formed structure with an urgency and efficiency that our models did not anticipate. It is a universe where the dark ages were brief, where the cosmic dawn was explosive, where galaxies matured in a cosmic eye blink. The physics of impossibility, why is it impossible for these galaxies to exist? The word impossible is strong, but it is justified by the physics. Let us examine in detail the specific physical barriers that should prevent the formation of such massive galaxies so early. First, the free fall time. When a region of gas begins to collapse under its own gravity, the timescale for collapse is determined by the density. The free fall time is proportional to 1 divided by the square root of the density. For a typical overdense region in the early universe at redshift 10, the density is about 1,000 times the cosmic mean density. The free fall time is roughly 50 million years. This is the time it takes for the gas to collapse from a diffuse state into a dense concentration. It is a hard limit set by gravity. You cannot make structure form faster than gravity pulls matter together. But collapse is only the first step. Once the gas is concentrated, it must cool. Hot gas has high thermal pressure, which resists further collapse. For star formation to occur, the gas must radiate away its thermal energy, cooling to temperatures of a few tens of degrees Kelvin. The cooling time depends on the density and temperature of the gas and the availability of coolants, atoms and molecules that can emit radiation. In the early universe, the primary coolants are hydrogen and helium. Atomic hydrogen can cool gas through Lyman alpha emission, but this is only efficient at temperatures above 10,000 degrees. Below that, molecular hydrogen becomes important. Molecular hydrogen can cool gas to much lower temperatures, enabling star formation. But molecular hydrogen is fragile, is easily destroyed by ultraviolet radiation. Once the first stars form and begin emitting ultraviolet light, they destroy molecular hydrogen in their surroundings, potentially suppressing further star formation. Moreover, cooling via molecular hydrogen is slow compared to cooling in metal-enriched gas. In the present-day universe, heavy elements like carbon and oxygen are extremely efficient coolants, allowing gas to cool quickly. In the early universe, with few heavy elements, cooling takes longer. The cooling time in primordial gas can be comparable to or longer than the free fall time, meaning that gas collapses as it cools, but the process is not rapid. These timescales, free fall time and cooling time, set a fundamental pace for star formation. Even under the most optimistic assumptions, you cannot turn gas into stars faster than the gas can collapse and cool. For a galaxy to assemble 100 billion solar masses of stars in 300 million years requires an average star formation rate of over 300 solar masses per year. Achieving this rate continuously for 300 million years requires a continuous supply of gas collapsing and cooling at this rate. The gas reservoir must be enormous, and the efficiency of converting gas into stars must be near 100%, with no losses to feedback. Second, the energy budget. Star formation releases energy. When gas collapses into stars, gravitational potential energy is converted into kinetic energy and heat. When stars undergo nuclear fusion, they release binding energy in the form of radiation. When massive stars explode as supernovae, they release approximately 10 to the 51 ergs of energy per explosion, most of it in the form of kinetic energy of the ejecta. A galaxy forming 1,000 solar masses of stars per year, with a typical initial mass function, will produce approximately 100 supernovae per year. Each supernova injects 10 to the 51 ergs into the surrounding gas. Over 100 million years, this amounts to 10 to the 61 ergs of energy. For comparison, the gravitational binding energy of a galaxy with a mass of 10 billion solar masses and a radius of 1 kiloparsec is roughly 10 to the 59 ergs. The energy injected by supernovae exceeds the binding energy of the galaxy by a factor of 100. This means that, in principle, supernova feedback can unbind all the gas in the galaxy, expelling it into intergalactic space and terminating star formation. For star formation to continue, the gas must somehow remain bound despite this energy input. This requires either that the energy is radiated away quickly, that it escapes the galaxy without coupling to the gas, or that the galaxy is much more massive and more tightly bound than typical early galaxies are expected to be. Simulations show that in small galaxies, supernova feedback is indeed very effective at expelling gas. Outflows with velocities of hundreds of kilometers per second are common, and much of the gas is lost. Only in more massive galaxies, with deeper gravitational potential wells, does the gas remain bound. But the halos available at redshift 10, according to the Standard Model, are not massive enough to retain gas in the face of such vigorous feedback. Third, the time for enrichment. The observed metallicities in some of the massive early galaxies indicate that the gas has been enriched to a significant fraction of solar metallicity. Solar metallicity means that about 2% of the gas mass is in elements heavier than helium. Achieving this level of enrichment requires that a substantial fraction of the gas has been cycled through stars, fused into heavy elements, and expelled back into the interstellar medium. The yield of heavy elements from a stellar population depends on the initial mass function and the fraction of the stellar mass that is returned to the interstellar medium. Typically, massive stars, which produce most of the heavy elements, return a large fraction of their mass to the surroundings when they explode. If 10% of the gas is turned into stars, and those stars return heavy elements with a yield of 2%, the metallicity increases by a fraction of the yield times the fraction of gas processed. To reach solar metallicity, essentially all the gas must be cycled through stars at least once, or multiple cycles with lower star formation efficiency are required. Each cycle takes time. A generation of stars must form, live, and die before the next generation can form from the enriched gas. Massive stars live for a few million years. If multiple generations are required, the total time is the sum of the lifetimes of each generation plus the time for gas to cool and collapse again between generations. Achieving solar metallicity in 300 million years requires very rapid cycling, with minimal delays between generations. This is difficult to reconcile with the disruptive effects of feedback, which should slow down the cycling by expelling gas and preventing immediate recollapse. Fourth, the merger timescale. Galaxies grow not only by forming stars within themselves, but also by merging with other galaxies. In the hierarchical model, Mergers are a key mechanism for building large galaxies. But mergers take time. Two galaxies must first be drawn together by gravity, orbiting around each other, gradually losing energy through dynamical friction, a process in which the galaxy's gravitational interactions with surrounding dark matter slow them down. The timescale for a merger depends on the masses and separations of the galaxies. For typical early galaxies, merger timescales are hundreds of millions of years. To build a galaxy of 100 billion solar masses by mergers alone would require numerous smaller galaxies to merge together. If each progenitor galaxy has a mass of 1 billion solar masses, 100 mergers are needed. These cannot all happen simultaneously. They must occur sequentially or in small groups, constrained by the orbital dynamics. The time required for this sequence of mergers is longer than the age of the universe at redshift 10. Even if mergers are happening as fast as dynamical friction allows, there is simply not enough time to assemble such massive galaxies through mergers alone. The physics of gravity, gas dynamics, stellar evolution, feedback, and chemical enrichment all impose fundamental timescales and energy limits on galaxy formation. The observed massive early galaxies appear to violate these limits, forming faster, more efficiently, and with less disruption than the laws of physics, as we understand them, permit. That is why they are deemed impossible. The redshift distribution. In excess everywhere, the tension between observation and theory is not confined to a handful of exceptionally massive galaxies. It extends across the entire population of galaxies at high redshift. Surveys with James Webb have measured the abundance of galaxies as a function of redshift and luminosity, constructing what is called the galaxy luminosity function, a statistical description of how many galaxies of each brightness exist at each epoch. At low redshift, the galaxy luminosity function is well established. It has a characteristic shape. Many faint galaxies, fewer bright galaxies, with the number of galaxies declining steeply at the bright end. This shape reflects the underlying distribution of dark matter halo masses and the efficiency of star formation as a function of halo mass. At high redshift, before James Webb, the luminosity function was poorly constrained. Hubble could detect only the brightest galaxies at redshift above 8. The faint end of the luminosity function, the small, dim galaxies expected to dominate by number, was beyond Hubble's reach. Theory predicted that at redshift 10, the luminosity function should shift to fainter luminosities overall, and the number density of bright galaxies should be very low, because massive galaxies had not yet had time to form. James Webb's observations have revealed that the bright end of the luminosity function at redshift 10 to 13 is higher than predicted. There are more bright galaxies than there should be. Quantitatively, the number density of galaxies with absolute magnitudes brighter than a certain threshold exceeds theoretical predictions by factors of 3 to 10 or more, depending on the exact redshift and luminosity range. This excess is not limited to the most extreme objects. It applies across the board. Even moderately bright galaxies, not just the most massive ones, are more abundant than expected. This suggests that the problem is not with a few outliers, exceptional objects that formed under rare circumstances, but with the entire process of galaxy formation in the early universe. Something about the way galaxies form at high redshift is fundamentally different from what we have assumed. One interpretation is that the star formation efficiency in the early universe is higher than in the present day. If a larger fraction of the gas in each dark matter halo is converted into stars, the galaxies will be brighter for a given halo mass, and the luminosity function will shift to higher luminosities. But why would star formation be more efficient early on? Feedback should be stronger, not weaker. Cooling should be less efficient, not more. There is no obvious physical reason for higher efficiency, and invoking it amounts to adjusting the model to fit the data without understanding the underlying cause. Another interpretation is that the dark matter halo mass function is different from predictions. If more massive halos exist at high redshift than the standard lambda-cold dark matter model predicts, then more massive galaxies can form. But as discussed earlier, Changing the halo mass function requires modifying the cosmological model in ways that affect many other observations. It is not a free parameter that can be adjusted without consequences. A third interpretation is that the relationship between halo mass and stellar mass is different at high redshift. Perhaps the processes that regulate star formation, feedback, gas accretion, cooling, operate differently in the extreme conditions of the early universe. Perhaps cold streams deliver gas more efficiently, bypassing feedback. Perhaps magnetic fields, turbulence, or other factors we have not fully accounted for change the dynamics. This is plausible, but it requires detailed physical modeling to determine whether such changes can produce the observed effects without conflicting with other constraints. The abundance of bright galaxies at high redshift is a statistical signal, less dramatic than individual massive galaxies, but arguably more significant. Individual objects can be outliers, rare fluctuations. But if the entire population is shifted to higher luminosities, this indicates a systematic difference between reality and theory, a difference that must be explained by modifying the physics of galaxy formation or the cosmological framework itself. The stellar mass function, a top-heavy puzzle parallel to the luminosity function, is the stellar mass function, the number density of galaxies as a function of their total stellar mass. While the luminosity function measures how bright galaxies are, which depends on current star formation and the age of stellar populations, the stellar mass function measures the accumulated result of star formation over the galaxy's history. It is a more direct probe of how much mass has been assembled. Measurements of the stellar mass function at high redshift are more uncertain than luminosity function measurements because determining stellar mass requires detailed modeling of the spectral energy distribution, as discussed earlier. Nonetheless, studies using James Webb data have constructed preliminary stellar mass functions at redshifts 10 to 13. The results show that the high mass end of the stellar mass function, the number density of galaxies with stellar masses above 10 billion solar masses, is elevated compared to theoretical predictions. The excess is similar in magnitude to the luminosity function excess, factors of a few to 10, depending on redshift and mass threshold. This is significant because stellar mass is a more fundamental quantity than luminosity. Luminosity can be affected by short-term variations in star formation, dust, or the presence of an active galactic nucleus. Stellar mass represents the integral of star formation over time. An excess in the stellar mass function means that the universe has produced more stars and massive galaxies by a given time than theory allows. Theoretical models predict that the stellar mass function should evolve in a specific way as a function of redshift, with a characteristic mass, the mass at which the number density of galaxies begins to decline steeply, shifting to lower masses at higher redshifts. This evolution reflects the hierarchical growth of structure. Small galaxies form first, and massive galaxies assemble later through mergers and continued star formation. But the observed stellar mass function at redshift 10 to 13 does not show the expected evolution. The high mass end is too populated. The characteristic mass is too high. The universe appears to have assembled massive galaxies too early, in direct contradiction to the hierarchical paradigm. Some models can reproduce the observed stellar mass function by tuning parameters, increasing star formation efficiency, reducing feedback strength, enhancing gas accretion rates. But these adjustments are ad hoc, not motivated by independent physical reasoning. They fit the data by force, not by understanding. What the stellar mass function tells us is that the problem is pervasive. It is not just that a few galaxies are too massive. It is that the entire population of massive galaxies at high redshift is more abundant than it should be. The universe's capacity to form stars and assemble them into large galaxies in the first few 100 million years is greater than our models predict. We are missing something fundamental about how galaxy formation proceeds in the early universe. The role of supermassive black holes compounding the mystery of massive early galaxies is the presence of supermassive black holes. Observations with James Webb and other telescopes have revealed active galactic nuclei, accreting supermassive black holes. At redshifts above 10, some with black hole masses estimated to be millions or even billions of solar masses. Supermassive black holes grow through two primary mechanisms: accretion of gas and mergers with other black holes. Accretion is limited by the Eddington limit, the maximum rate at which a black hole can accrete matter, while the radiation pressure from the accretion disk does not blow away the infalling material. For a black hole of a given mass, the Eddington-limited accretion rate produces a corresponding maximum luminosity. Integrating this rate over time gives a maximum mass that a black hole can reach as a function of time. If a black hole seed forms at redshift 30 with a mass of 100 solar masses, perhaps as the remnant of a population 3 star, and accretes continuously at the Eddington limit, it can grow exponentially, doubling its mass every few tens of millions of years. By redshift 10, about 500 million years later, it could reach a mass of approximately 100 million solar masses, possibly more if accretion proceeds above the Eddington limit in dense environments. But black holes with masses of 1 billion solar masses or more require either much larger seed masses or much longer times, or some mechanism for super Eddington accretion. Finding such massive black holes at redshift 10 or higher suggests that black hole growth, like galaxy growth, is proceeding faster than expected. The relationship between black hole mass and host galaxy stellar mass is well established in the nearby universe. Supermassive black holes in the centers of galaxies have masses that are roughly 0.1% of the stellar mass of the galaxy's bulge. This relationship implies a connection between black hole growth and galaxy growth, mediated by processes such as gas inflow, star formation, and feedback from the black hole itself. In the massive early galaxies observed by James Webb, if this relationship holds, the black holes should have masses proportional to the stellar masses. A galaxy with 100 billion solar masses should host a black hole of 100 million solar masses. Observational evidence for such black holes exists in some cases, but the relationship is less clear at high redshift. Some galaxies appear to have black holes that are more massive relative to their stellar mass than in the present-day universe, suggesting that black holes may grow faster than galaxies in the early universe, or that the relationship evolves with redshift. The presence of massive black holes adds another layer to the impossibility problem. Not only must the galaxies form stars at an unprecedented rate, but they must also grow their central black holes to enormous sizes in the same brief interval. The two processes are linked. Both require gas to flow into the center of the galaxy. Both release energy that can affect the surrounding environment, but the details of how they operate together in the early universe are not well understood. Active galactic nuclei can also contribute to the feedback that regulates star formation. The energy released by an accreting black hole, in the form of radiation, winds, and jets, can heat and expel gas from the galaxy, potentially quenching star formation. This so-called AGN feedback is thought to be important in massive galaxies in the present-day universe, preventing them from forming too many stars. But if AGN feedback is strong in the early universe, it should limit galaxy growth, making the observed massive galaxies even more difficult to explain. If AGN feedback is weak or absent, this could allow more efficient star formation, but then we must explain why feedback would be weaker in the early universe. The interplay between black hole growth, star formation, and feedback in the early universe is complex, and the observations from James Webb are only beginning to constrain the relevant processes. What is clear is that both galaxies and black holes are growing faster than theory predicts, suggesting that the conditions in the early universe enable rapid assembly of both stellar and black hole mass in ways that challenge our understanding. Reionization and the impact of massive galaxies, the massive early galaxies discovered by James Webb, have implications beyond their own existence. They affect the broader history of the universe, particularly the reionization of hydrogen. After recombination, the universe was filled with neutral hydrogen atoms. As the first stars and galaxies formed, they emitted ultraviolet radiation capable of ionizing hydrogen, stripping electrons from atoms, turning neutral hydrogen into ionized hydrogen plasma. This process, called reionization, gradually transformed the universe from neutral to ionized, creating expanding bubbles of ionized gas around each source of radiation. As these bubbles grew and overlapped, the intergalactic medium transitioned from mostly neutral to mostly ionized. Observations of the spectra of distant quasars show absorption features caused by neutral hydrogen along the line of sight. The amount of absorption indicates how much neutral hydrogen is present at different redshifts. These observations tell us that reionization was largely complete by redshift 6, about 1 billion years after the Big Bang. Before that, the universe was increasingly neutral, with reionization likely beginning at redshifts above 10. The sources of ionizing radiation responsible for reionization are thought to be primarily stars and galaxies. The more galaxies there are, and the more massive and actively star-forming they are, the more ionizing photons are produced. Prior to James Webb, models of reionization assumed that the ionizing photon budget was dominated by small, faint galaxies, because these were thought to be the most numerous. Massive galaxies were expected to be rare at high redshift and thus contribute less. But if massive galaxies are more abundant than expected, and if they are forming stars at high rates, they produce a larger number of ionizing photons. This means the reionization history could be different from previous models predicted. Reionization might begin earlier, proceed faster, or be dominated by more massive sources. Measurements of the optical depth of the cosmic microwave background, how much it is scattered by free electrons along the line of sight, provide a constraint on the integrated ionization history. The Planck satellite measured an optical depth consistent with reionization occurring around redshift 8 to 10. If reionization occurred significantly earlier or faster, the optical depth would be higher. So far, the James Webb findings do not appear to violate this constraint, but they are close to the edge of what is allowed. More detailed studies of reionization are ongoing. Astronomers are using James Webb to map the sizes and shapes of ionized regions around early galaxies, studying how the ionizing radiation escapes from galaxies into the intergalactic medium, and measuring the ionizing photon production efficiency of high redshift galaxies. The picture emerging is that massive galaxies may contribute more to reionization than previously thought, but the faint galaxy population remains important. The existence of abundant massive galaxies at redshift 10 also affects the chemical enrichment of the intergalactic medium. Stars in these galaxies produce heavy elements, which are expelled into the surrounding space by supernova-driven winds. These metals mix with the intergalactic gas, enriching it. Observations of metal absorption lines in quasar spectra show that by redshift 6, the intergalactic medium has a metallicity of about 1/10 of 1% of solar. If massive galaxies are abundant at redshift 10, they could contribute significantly to this enrichment, potentially requiring models of metal mixing and transport to be revised. The massive galaxies also affect the growth of structure on larger scales. Their gravitational pull influences the motion of surrounding matter, the formation of cosmic filaments, and the clustering of other galaxies. If the high-mass end of the galaxy population is more abundant than expected, the large-scale structure of the universe at high redshift might be different from models predict. Future observations, mapping the three-dimensional distribution of galaxies at redshift 10 and beyond, will test whether the clustering properties match theoretical expectations. Lensing, nature's magnifying glass, one of the most powerful tools for studying distant galaxies, is gravitational lensing. According to general relativity, mass warps space-time, bending the path of light. When a massive object, such as a galaxy cluster, lies between us and a more distant galaxy, the cluster's gravity acts as a lens, magnifying and distorting the image of the distant galaxy. Gravitational lensing allows astronomers to study galaxies that would otherwise be too faint to detect. A galaxy at redshift 10, magnified by a factor of 10 by a foreground cluster, becomes as bright as a galaxy 10 times closer. This magnification brings distant galaxies within reach of detailed observations, enabling spectroscopy and high-resolution imaging that would not be possible otherwise. James Webb has exploited gravitational lensing extensively in its studies of the early universe. Deep observations of galaxy clusters, such as those from the Glass, Uncover, and other programs have revealed hundreds of lensed high-redshift galaxies. Some of the most massive early galaxies discovered by James Webb were found in lensing fields, their light amplified by the gravitational potential of the intervening cluster. Lensing also provides an independent check on mass estimates. The magnification factor depends on the mass of the lensing cluster and the geometry of the lensing configuration, both of which can be modeled using observations of multiple lensed images and the distribution of galaxies in the cluster. By comparing the observed brightness of a lensed galaxy to the expected brightness based on the magnification, astronomers can verify that their models are accurate. If the intrinsic brightness or mass of the galaxy were overestimated, the lensing magnification would not match expectations. Studies of lensed galaxies have confirmed that many of the massive early galaxies are indeed as bright and as massive as unlensed observations suggest. The lensing magnification allows these galaxies to be studied in finer detail, revealing internal structure, star-forming regions, and sometimes even gravitationally bound clumps that might be protoglobular clusters or satellite galaxies in the process of merging. One particularly intriguing lensed galaxy, observed at redshift approximately 12, shows a compact core surrounded by a more extended envelope. The core is extremely dense, with a stellar mass surface density comparable to the densest present-day galaxies. The envelope contains younger stars and ongoing star formation. The structure suggests that the galaxy is building up from the inside out, with a central concentration forming first and additional mass accreting onto it over time. This inside-out growth is consistent with some models of galaxy formation, but the timescale remains puzzlingly short. Another lensed galaxy, at redshift 13, has been magnified to the point where individual star-forming regions are resolved. The regions are only a few tens of parsecs across, each forming stars at rates of several solar masses per year. The total star formation rate across the entire galaxy exceeds 1,000 solar masses per year. The galaxy is a cosmic construction site, assembling its stellar mass at a furious pace. And yet, even this extreme rate, sustained for the available time, barely produces the observed stellar mass, underscoring how tight the time constraint is. Gravitational lensing has not resolved the paradox of massive early galaxies. Instead, it has sharpened it, providing clearer, more detailed views of objects that should not exist, confirming their properties with greater certainty and deepening the mystery. The theoretical counteroffensive, modified models in response to the James Webb discoveries. Theorists have launched an intensive effort to modify models of galaxy formation to accommodate the observations. This effort has produced a variety of proposed solutions, each addressing different aspects of the problem. One class of models focuses on enhancing star formation efficiency. These models propose that in the dense, gas-rich environments of the early universe, star formation proceeds more rapidly than in the present day. Mechanisms suggested include reduced feedback due to the geometry of gas accretion, enhanced gravitational instability in gas-rich disks leading to rapid fragmentation and star formation, and the role of turbulence in concentrating gas into dense clumps where stars form. Some models invoke strong gravitational torques from cosmic filaments, which funnel gas into the centers of galaxies at very high rates, overwhelming feedback and enabling sustained star formation. Others suggest that the first stellar populations might have had a different initial mass function, producing fewer low-mass stars and more intermediate-mass stars, which would increase the light-to-mass ratio and reduce the inferred stellar masses, though, as discussed earlier, this does not fully resolve the discrepancy. Another class of models focuses on the merger history. Perhaps galaxies in the early universe merged more rapidly than standard models predict, accelerating the assembly of stellar mass. This could occur if the halos are more concentrated, reducing dynamical friction timescales, or if gas-rich mergers are more common, leading to starbursts that rapidly build up mass. A third class of models revisits the role of dark matter. Proposals include warm dark matter with specific particle properties that suppress structure on the smallest scales but allow rapid growth on intermediate scales, self-interacting dark matter that alters halo density profiles and merger rates, and even more exotic possibilities, such as primordial black holes contributing to the dark matter, potentially affecting both halo growth and the formation of supermassive black holes. Some theorists have explored modifications to the expansion history of the universe. Early dark energy models, in which dark energy is not constant but has a different equation of state in the early universe, could alter the relationship between redshift and cosmic time, providing more time for galaxies to form. However, these models are tightly constrained by cosmic microwave background and other observations, and most do not survive scrutiny. Another avenue is to revisit the initial conditions set by inflation. If the primordial power spectrum, the distribution of density fluctuations as a function of scale, has more power on small scales than the standard power law form assumes, this could lead to earlier and more rapid structure formation. Such a modification could arise from features in the inflationary potential or from non-standard inflationary dynamics. But any change to the primordial power spectrum must be consistent with observations of the cosmic microwave background, large-scale structure, and the abundances of rare massive clusters, which collectively constrain the spectrum tightly. Each of these proposed solutions has strengths and weaknesses. Many can reproduce some aspects of the observations, but fail to match others. Some introduce new parameters that are not well constrained. Others conflict with observations in different contexts. The theoretical community is actively testing these ideas, running simulations, comparing predictions to data, and refining models. What is clear is that simple tweaks are insufficient. The discrepancy between observation and theory is too large to be resolved by minor adjustments. Either there is a fundamental misunderstanding of the physics of star formation and feedback in the early universe, or there is something wrong with the cosmological framework within which galaxies form. Both possibilities are profound. The observational roadmap. What comes next? The James Webb Space Telescope has only just begun its mission. The observations that revealed the massive early galaxies were conducted in the first year of operations, using only a fraction of the telescope's allocated time. Much more data is coming. Several large survey programs are underway to map the high redshift universe in unprecedented detail. The Cosmos Web Survey is imaging a large area of sky to moderate depth, aiming to find thousands of galaxies at redshifts above 6 and hundreds at redshifts above 10. The JWST Advanced Deep Extragalactic Survey program is conducting ultra-deep observations of smaller fields, reaching fainter galaxies and higher redshifts. The Primer Public Release Imaging for Extragalactic Research survey is combining imaging and spectroscopy to characterize the galaxy population across cosmic time. These surveys will provide much larger samples of high redshift galaxies, allowing statisticians to measure the luminosity and stellar mass functions with greater precision, characterize the diversity of galaxy properties, and identify rare objects that may represent different formation channels or environments. Spectroscopic follow-up will continue, targeting candidates identified in imaging surveys to confirm redshifts and measure physical properties. The NIR SPEC instrument can observe dozens of galaxies simultaneously, making it possible to obtain spectra of large samples efficiently. Spectroscopy reveals star formation rates, metallicities, ionization states, gas kinematics, and the presence of active galactic nuclei, providing a comprehensive view of galaxy physics. High-resolution imaging with NIRCam and MIRI will probe the internal structure of galaxies, looking for signs of disks, bulges, bars, mergers, and other morphological features. Understanding the structure of early galaxies constrains models of how they assembled, whether through smooth accretion, violent mergers, or internal processes. Observations in the mid-infrared with MIRI will measure dust emission and constrain dust masses and temperatures. This addresses one of the key uncertainties in stellar mass estimates and reveals the role of dust in the early universe. Mid-infrared spectroscopy can also detect emission lines from molecules and fine structure transitions of atoms, probing the conditions in the interstellar medium. Combining James Webb data with observations from other facilities will provide complementary information. The Atacama Large Millimeter Array, ALMA, can observe the far-infrared and submillimeter emission from dust and molecular gas, measuring gas masses and kinematics. Ground-based, near-infrared spectrographs can obtain high-resolution spectra of the brightest targets. Future space missions, such as the Nancy Grace Roman Space Telescope, will provide wide-field imaging and spectroscopy, discovering even more high-redshift galaxies and placing them in a broader cosmological context. Theoretical work will continue in parallel. Simulations of galaxy formation are being rerun with modified physics, higher resolution, and improved models of star formation and feedback. Comparisons between simulations and observations will refine our understanding of what processes are most important and where the models fail. Machine learning and statistical techniques are being applied to large data sets to identify patterns, classify galaxies, and predict properties. These methods can handle the complexity and volume of data that James Webb is producing, enabling discoveries that might be missed by traditional analysis. The roadmap is clear: more observations, deeper analysis, broader comparisons, iterative refinement of theory. Over the next few years, the picture will come into sharper focus. We will learn whether the massive early galaxies are truly as common and as massive as initial results suggest, or whether selection effects, observational biases, or systematic errors have led to overestimates. We will learn what physical processes enable such rapid galaxy formation and whether they require new physics or simply a better understanding of known processes. We will learn whether the cosmological model needs revision or whether the problem lies entirely within the realm of astrophysics. The philosophical weight of the discovery beyond the technical details and the scientific debate, the discovery of massive early galaxies carries a philosophical weight. It reminds us that the universe does not conform to our expectations, that our models, no matter how successful, are approximations, and that nature holds surprises that force us to rethink what we thought we knew. For decades, cosmology has been on a trajectory of increasing precision. The parameters of the Standard Model have been measured with exquisite accuracy. The timeline of cosmic history has been mapped with confidence. The narrative of structure formation, from tiny quantum fluctuations to vast cosmic webs, has been told and retold, refined and tested. There is a sense, perhaps, that the broad outlines were settled, that future work would fill in details but not overturn fundamentals. James Webb has disrupted that sense. It has found something that does not fit, something that challenges the foundations. The massive early galaxies are an anomaly in the Kuhnian sense, an observation that cannot be assimilated into the prevailing paradigm without significant modification. Whether this anomaly will lead to a revolution, a shift in the paradigm itself, or whether it will be accommodated through adjustments within the existing framework, remains to be seen. The history of science is filled with such moments. The perihelion precession of Mercury, unexplained by Newtonian gravity, was resolved by general relativity. The blackbody spectrum of thermal radiation, inconsistent with classical physics, led to quantum mechanics. The accelerating expansion of a universe, unexpected and inexplicable in a matter-dominated cosmos, led to the concept of dark energy. Each of these anomalies forced a conceptual leap, a willingness to abandon cherished assumptions and embrace new principles. Perhaps the massive early galaxies will lead to a similar leap. Perhaps they are telling us that the lambda cold dark matter model, for all its successes, is missing something essential. Perhaps they are revealing new physics in the dark sector, or in the behavior of gravity on cosmological scales, or in the initial conditions of the universe. Or perhaps they are simply telling us that the astrophysics of galaxy formation is far richer and more complex than we imagined, that the interplay of gas, stars, dark matter, and feedback in the extreme conditions of the early universe produces phenomena we have not yet learned to model. Whatever the resolution, The discovery is humbling. It is a reminder that the universe is older, larger, and stranger than our minds can fully grasp, that each advance in observational capability reveals new mysteries, and that the quest to understand the cosmos is an unending journey. The silence of the giants imagine standing in the dark, looking up at the night sky. The stars you see are nearby, within our own galaxy, mere thousands of light years away. The faint smudges of light, visible only with a telescope, are distant galaxies, millions or billions of light years away. Their light has traveled across the expanding universe, carrying information about the past. Now, imagine looking deeper, past the nearby galaxies, past the distant ones, to the very edge of the observable universe. You are looking back in time toward the moment of the Big Bang itself. The light you see is the oldest light in the universe, emitted when the first stars ignited and the first galaxies assembled. And there, in that ancient darkness, you find giants. Galaxies that should not exist. Galaxies so massive, so bright, so structured, that they defy explanation. They are silent, their stars long dead, their light redshifted into invisibility to the unaided eye. But James Webb sees them, and in seeing them, it asks a question that echoes across the cosmos. How? How did these galaxies form so quickly? How did they accumulate so much mass in so little time? How did they evade the mechanisms that should have prevented their formation? How did the universe, barely out of its infancy, produce structures of such grandeur? We do not yet have answers. We have clues, hints, possibilities. We have data, models, simulations. We have the tools of science, observation, theory, experiment, iteration. But the mystery remains. Perhaps the answer lies in the details of star formation, in the efficiency of gas cooling in dense environments, in the role of cosmic filaments channeling gas into galaxies. Perhaps it lies in the properties of dark matter, in interactions or dynamics we have not yet understood. Perhaps it lies in the initial conditions, in the seeds planted by inflation, in the structure of the quantum fluctuations that became galaxies. Perhaps it lies in the expansion history, in a phase of the universe we have not yet discovered. Perhaps it lies somewhere we have not yet thought to look. The massive early galaxies are an invitation to question, to explore, to imagine. An invitation to push the boundaries of knowledge, to confront the limits of our understanding, to venture into the unknown. The hierarchical paradigm under siege, the hierarchical model of structure formation, is one of the cornerstones of modern cosmology. It is the framework within which we understand how the universe evolved from a nearly uniform state to the rich tapestry of galaxies, clusters, and voids we observe today. The model is simple in concept. Small structures form first, then merge to form larger structures, and so on, building up the hierarchy from the bottom up. This model is not arbitrary. It emerges naturally from the physics of gravitational collapse in an expanding universe dominated by cold dark matter. In the early universe, density fluctuations on all scales begin to grow under gravity. But smaller scale fluctuations have higher densities and collapse faster. By the time large-scale fluctuations are beginning to condense, small-scale fluctuations have already collapsed into bound objects. These small objects then merge to form larger ones, and the process continues. Observations have largely supported this picture. The clustering of galaxies on large scales matches the predictions of hierarchical models. The abundance of galaxy clusters as a function of mass and redshift follows the expected evolution. The properties of galaxies, sizes, masses, star formation rates, show trends with redshift that are consistent with gradual assembly through mergers and gas accretion. But the massive early galaxies discovered by James Webb do not fit this picture. They're too large, too early. They suggest that, at least in some cases, large structures form directly, not through the slow hierarchical buildup of smaller components. This is not hierarchical formation. It is something else. One possibility is that these galaxies are the result of exceptionally rare density fluctuations, peaks in the primordial density field that were so overdense that they collapsed and formed massive halos very early. In the Standard Model, such rare peaks do exist, but they are exponentially rare. Finding multiple examples in the relatively small volume surveyed by James Webb suggests that they are more common than expected, which again implies that something is different about the initial conditions or the growth of structure. Another possibility is that these galaxies formed through a different channel, not by hierarchical mergers, but by the direct collapse of massive gas clouds. In the early universe, when the gas was denser and more homogeneous, conditions might have allowed entire clouds containing billions of solar masses of gas to collapse coherently, forming a massive galaxy in one go. This process, sometimes called monolithic collapse, was considered decades ago, but fell out of favor as hierarchical models became dominant. The James Webb discoveries have revived interest in it. Monolithic collapse requires special conditions. The gas cloud must be large enough and dense enough to collapse under its own gravity, but it must also be able to cool efficiently to radiate away the gravitational energy released during collapse. In the primordial gas of the early universe, cooling is slow, as discussed earlier. But if the gas has been pre-enriched with even trace amounts of heavy elements by an earlier generation of stars, cooling becomes more efficient, enabling collapse. This suggests a two-stage process. First, a burst of star formation enriches the gas. Then, the enriched gas collapses to form a massive galaxy. The timescale is still tight, but perhaps not impossible. Another scenario involves direct collapsed black holes. If conditions in the early universe allow gas clouds to collapse directly into black holes without forming stars first, bypassing the normal stellar evolution pathway, these black holes can have masses of thousands or even millions of solar masses from the outset. Such massive seeds can grow more quickly into supermassive black holes, and they can also influence the formation of the surrounding galaxy by accreting gas, releasing energy, and potentially triggering star formation in their vicinity. This could lead to the rapid assembly of a massive galaxy around a massive black hole, with the two growing in tandem. Each of these alternatives to the hierarchical paradigm has implications and challenges. They require specific conditions that may or may not be met in the early universe. They predict observable signatures, distributions of galaxy properties, clustering patterns, relationships between stellar mass and halo mass that can be tested against data. The work of testing these alternatives is ongoing. What is clear is that the hierarchical paradigm, while successful in many contexts, is under siege. It is being questioned, tested, and potentially revised. Whether it will be overthrown or simply refined depends on the outcomes of future observations and theoretical work. The multi-wavelength perspective, beyond the infrared James Webb, observes the universe primarily in the infrared, but understanding the massive early galaxies requires observations across the entire electromagnetic spectrum. Each wavelength regime provides different information about the physical processes at work. In the ultraviolet, rest frame emission from hot, massive stars traces the current star formation rate. For high redshift galaxies, the ultraviolet light is redshifted into the optical or near-infrared, where James Webb can observe it. But some galaxies are so distant that their ultraviolet light is redshifted beyond James Webb's range, requiring observations at even longer wavelengths. In the optical, rest frame emission traces the older stellar populations and provides information about the galaxy's integrated star formation history. Optical spectroscopy reveals emission lines from ionized gas, which constrain star formation rates, metallicities, and the ionizing photon output. In the near-infrared, rest frame emission traces cooler stars and dust-reprocessed starlight. This is the regime where James Webb excels, providing high sensitivity and spatial resolution. The shapes of spectral energy distributions in the near-infrared are key to determining stellar masses. In the mid-infrared, emission from warm dust dominates. This dust is heated by starlight and re-emits the energy at longer wavelengths. Mid-infrared observations constrain dust masses and temperatures, and they can reveal obscured star formation that is hidden at shorter wavelengths. The MIRI instrument on James Webb provides unprecedented sensitivity in this regime. In the far-infrared and submillimeter, emission from cold dust traces the reservoirs of gas and dust available for future star formation. Observations with ALMA and other ground-based facilities are crucial for measuring gas masses and kinematics, which inform models of how gas is supplied to galaxies and how it is converted into stars. At radio wavelengths, emission from synchrotron radiation and free emission traces star formation and supernova activity. Radio observations can penetrate dust and provide independent estimates of star formation rates. Future radio telescopes, such as the Square Kilometer Array, will extend these observations to high redshifts. At X-ray wavelengths, emission from hot gas and accreting black holes provides information about the high-energy processes in galaxies. X-ray observations can detect active galactic nuclei even when they are obscured by dust. They can also trace the hot gas and galaxy halos and the energy injected by feedback. Combining observations across all these wavelengths provides a comprehensive view of galaxy properties. Multi-wavelength studies of the massive early galaxies are revealing details that single-wavelength observations cannot capture. For example, some galaxies that appear red and quiescent in the near-infrared show evidence of active star formation in the mid-infrared or submillimeter, indicating that they are dust-obscured starbursts rather than truly quenched systems. Others show X-ray emission from active galactic nuclei, indicating that black hole growth is contributing to their luminosity. The multi-wavelength perspective also helps to break degeneracies in models. A given near-infrared spectral energy distribution might be fit equally well by an old, dusty stellar population or by a young, dust-free population with an unusual initial mass function. But the addition of mid-infrared or submillimeter data can distinguish between these possibilities by measuring the dust emission directly. Multi-wavelength observations are logistically challenging, requiring coordination between different telescopes and instruments, often on different timescales. But they are essential for a complete understanding of the massive early galaxies and the physical processes that govern their formation and evolution. The statistical significance. Are these galaxies real outliers or a new norm? When a surprising discovery is made, one of the first questions is whether it is statistically significant. Are the massive early galaxies genuine outliers, rare flukes that happen to have been caught in the relatively small volume surveyed so far? Or do they represent a new norm, indicating that the galaxy population at high redshift is systematically different from what was expected? To answer this, astronomers conduct statistical analyses, calculating the probability that such objects would be observed given the predictions of theoretical models. If the probability is very low, less than 1 in 1,000, for example, the observations are considered statistically significant, and the models are considered to be in tension with the data. Calculations show that the probability of observing multiple galaxies with stellar masses above 10 billion solar masses at redshifts 10 to 13, given the predictions of the standard lambda cold dark matter model, is extremely low. Depending on the exact assumptions about star formation efficiency and feedback, the probability ranges from less than 1% to less than 1 in 10,000. This is a strong statistical tension, suggesting that the observations are not simply the result of chance fluctuations. However, statistical significance must be interpreted carefully. Low probabilities do not necessarily mean the model is wrong. They could mean that the survey happened to intersect a rare, overdense region of the universe, where galaxies are more abundant than average. The universe is not uniform. It has regions of higher and lower density due to the primordial fluctuations. If the James Webb surveys happen to target an overdense region, the observed galaxy counts could be higher than the cosmic average. To test this, astronomers compare observations from multiple independent fields in different parts of the sky. If the excess of massive galaxies is seen in all fields, it is a global effect, indicating that the models need to be revised. If the excess is seen in only 1 or 2 fields, it might be a local fluctuation, less significant for cosmology. So far, the excess appears to be present in multiple fields. Surveys covering different areas of sky, observed with different instruments and analyzed by independent teams, all find more bright, massive galaxies at high redshift than expected. This suggests that the effect is real and global, not a local anomaly. Another statistical consideration is the role of systematic errors. Could uncertainties in photometric redshifts, stellar mass estimates, or other derived quantities systematically bias the results? As discussed earlier, various sources of uncertainty have been explored, and while they affect the exact numbers, they do not eliminate the discrepancy. The statistical significance remains. The statistical evidence supports the conclusion that the massive early galaxies are not rare outliers, but a genuine feature of the high redshift galaxy population. They are more common than theory predicts, and they represent a real challenge to our models. The cosmic variance problem related to statistical significance is the issue of cosmic variance. The universe is not perfectly uniform. The distribution of galaxies is clumpy, with regions of high density, clusters and superclusters, and regions of low density, voids. When we observe a small volume of the universe, the number of galaxies we count is subject to fluctuations due to this clumpiness. This source of uncertainty is called cosmic variance. Cosmic variance is particularly important for studies of rare objects. Massive galaxies at high redshift are rare by any measure. If they are more abundant in overdense regions and less abundant in underdense regions, then the number we observe in a given survey depends on whether the survey volume happens to intersect an overdense region. Small survey volumes have large cosmic variance, meaning the observed galaxy counts can deviate significantly from the cosmic average. James Webb's deep surveys observe relatively small areas of sky, on the order of tens of square arcminutes, to reach faint galaxies at high redshift. These small areas correspond to small comoving volumes at redshift 10, increasing the cosmic variance. It is possible that some of the observed massive galaxies are in overdense regions, leading to higher counts than would be typical for the universe as a whole. To mitigate cosmic variance, astronomers conduct multiple surveys in different regions of the sky and combine the results. They also use simulations to estimate the expected level of cosmic variance for a given survey geometry and compare the observed variance to expectations. If the observed variance is consistent with simulations, it suggests that cosmic variance alone cannot explain the high counts, and a genuine excess exists. Early results indicate that even accounting for cosmic variance, the number of massive early galaxies exceeds predictions. The excess is not simply bad luck in field selection, but more data from additional survey fields will help to quantify this more precisely. Cosmic variance is both a challenge and an opportunity. It is a source of uncertainty that complicates the interpretation of observations. But it also contains information about the distribution of matter in the universe, the growth of structure, and the clustering properties of galaxies. By studying the degree of cosmic variance in the high redshift galaxy population, astronomers can learn about the underlying dark matter distribution and test models of structure formation. The role of environment. Where do these galaxies live? Galaxy formation is not independent of environment. Galaxies in dense regions, such as protoclusters, experience more frequent interactions and mergers, have access to larger gas reservoirs, and are influenced by the gravitational potential of the surrounding matter. Galaxies in underdense regions, in voids or filaments, evolve more in isolation. The massive early galaxies discovered by James Webb raise the question, where do they live? Are they in special environments that facilitate their rapid growth, or are they distributed randomly throughout the universe? Some studies have found evidence that massive high redshift galaxies are preferentially located in overdense regions, protoclusters that will eventually collapse to form galaxy clusters by the present day. This makes sense in the hierarchical model. Overdense regions have higher dark matter halo masses, more gas, and more vigorous star formation. If the massive galaxies are in protoclusters, it suggests that environment plays a key role in their formation. Other studies find massive galaxies in relatively isolated environments, far from other bright galaxies. This is more puzzling. If a galaxy is isolated, it has fewer neighbors to merge with, less opportunity to accrete gas from its surroundings, and less environmental pressure to trigger star formation. How then does it become so massive so quickly? One possibility is that these isolated massive galaxies are the central galaxies of the most massive dark matter halos at high redshift. Even without merging with other galaxies, they can grow by accreting gas from the intergalactic medium along cosmic filaments. If the gas supply is sufficiently rich and the star formation efficiency sufficiently high, a single galaxy can accumulate a large stellar mass without mergers. Another possibility is that the apparent isolation is misleading. High redshift galaxies are difficult to detect, and surveys may miss faint companions that are actually present. What appears as an isolated galaxy might actually be the brightest member of a small group or the central galaxy of a protocluster whose other members are below the detection threshold. To address this, astronomers are conducting targeted studies of the environments of massive early galaxies, searching for companions, measuring the density of galaxies in the surrounding region, and comparing to simulations to determine whether the observed environments are typical or extreme. Understanding the role of environment is crucial for models of galaxy formation. If massive galaxies form only in special environments, models can focus on those conditions and explore the specific mechanisms at work. If they form everywhere, models must explain how ordinary environments can produce extraordinary results. The quenching question: are some of these galaxies dead? Among the most surprising findings from James Webb is evidence that some massive early galaxies have ceased forming stars. They're quenched. Their spectral energy distributions are dominated by red, evolved stars, with little or no emission from young, blue stars. Their spectra lack strong emission lines from ionized gas, indicating that star formation has stopped or is at very low levels. Quenched galaxies are common in the present-day universe, especially among the most massive galaxies. They have exhausted or expelled their gas supply, or star formation has been suppressed by some mechanism, such as feedback from an active galactic nucleus or the heating of gas in the galaxy halo. But finding quenched galaxies at redshift 10 or higher, only a few 100 million years after the Big Bang, is unexpected. To understand why, consider the life cycle of a galaxy. A galaxy forms stars as long as it has a supply of cold gas. Star formation continues until the gas is consumed, expelled, or heated to the point where it can no longer collapse. In the present-day universe, quenching occurs in massive galaxies when the gas is heated by shocks as it falls into the deep gravitational potential well of the halo, or when an active galactic nucleus injects energy into the gas, preventing cooling and star formation. But these quenching mechanisms require time to operate. Gas heating by shocks is most effective in massive halos, which take time to assemble. Active galactic nuclei require supermassive black holes, which take time to grow. In the early universe, halos are smaller, black holes are younger, and quenching should be less effective. Galaxies should be forming stars vigorously, not quenched. The presence of quenched galaxies at high redshift suggests that quenching can occur very quickly, perhaps through processes that are more efficient in the early universe than they are today. One possibility is that the first burst of star formation is so intense that it rapidly consumes or expels all the available gas, leaving the galaxy quenched. Another is that early active galactic nuclei are more powerful or more efficient at heating gas than their present-day counterparts. Alternatively, the quenching might be temporary. A galaxy might form stars in a burst, quench for a period as the gas is heated and expelled, then reignite star formation as the gas cools and falls back in. Such cycles of star formation and quenching could lead to galaxies with red colors and old stellar populations at certain times, even though they later resume star formation. Observations of such galaxies over time, impossible with James Webb, but possible in simulations, show complex histories of bursts, quenching, and reactivation. The existence of quenched galaxies at high redshift also has implications for the stellar mass function and the abundance of massive galaxies. Quenched galaxies contribute to the stellar mass of the universe, but are often faint and difficult to detect because they lack the bright emission from ongoing star formation. If a significant fraction of the stellar mass at high redshift is in quenched galaxies, surveys might be underestimating the total stellar mass density, making the discrepancy with models even larger. Studying quenched galaxies at high redshift is challenging because they are faint, but James Webb sensitivity makes it possible. Spectroscopy can measure the stellar ages, confirming whether the galaxies have truly stopped forming stars or are merely in a lull. High-resolution imaging can probe their structure, looking for signs of recent mergers or interactions that might have triggered quenching. Multi-wavelength observations can constrain the presence of gas, dust, and active galactic nuclei. The quenching question is a frontier in the study of high-redshift galaxies, and it adds yet another layer to the mystery of how these galaxies formed and evolved so rapidly. The initial mass function debate. Are stars different in the early universe? The initial mass function describes the distribution of stellar masses that form from a collapsing gas cloud. It is a fundamental input to models of galaxy evolution, determining how much light and how much feedback a given mass of stars produces, how quickly chemical enrichment occurs, and how stellar populations evolve over time. In the local universe, the initial mass function is reasonably well constrained. Observations of stellar populations in the Milky Way and nearby galaxies show that for every massive star, there are many more low-mass stars. The exact form varies, but a common parametrization is the Salpeter IMF or the Kropa IMF, both of which have power law slopes with more low-mass stars than high-mass stars. This bottom-heavy IMF means that most of the stellar mass is in low-mass stars, but most of the light and most of the feedback come from the rare massive stars. If the initial mass function in the early universe is the same as today, then the interpretation of the light from early galaxies is straightforward. But if the initial mass function is different, for example, top-heavy, with more massive stars relative to low-mass stars, then the same amount of light could come from a smaller total stellar mass, because massive stars are much brighter. There are theoretical reasons to expect the initial mass function might be different in the early universe. The gas is metal-poor, lacking the heavy elements that help cool gas clouds and allow the fragmentation that leads to low-mass stars. Without efficient cooling, collapsing clouds might fragment less, forming fewer, more massive stars. The first generation of stars, population 3 stars, are expected to have a top-heavy initial mass function for this reason. But by the time the massive galaxies observed by James Webb were forming at redshifts 10 to 13, the gas was no longer completely pristine. It had been enriched by at least some previous generation of stars, introducing heavy elements that enable cooling. It is unclear whether this enrichment is sufficient to produce an initial mass function similar to the present day, or whether the lower metallicity still biases the initial mass function toward more massive stars. Observational constraints on the initial mass function at high redshift are difficult to obtain. Direct observation of individual stars is impossible. We can only infer the initial mass function from the integrated light of entire galaxies. Different initial mass functions produce different spectral energy distributions, emission line strengths, and colors. By comparing observations to models with varying initial mass functions, astronomers can attempt to constrain the initial mass function. Studies of the massive early galaxies using this approach yield mixed results. Some galaxies are consistent with a standard bottom-heavy initial mass function. Others seem to require a top-heavy initial mass function to explain their observed properties. The uncertainty is large, and the debate continues. If the initial mass function is top-heavy, the implications are significant. The stellar masses inferred from the light would be overestimates, perhaps by factors of a few. This would reduce the discrepancy with theoretical predictions, though, as mentioned earlier, it would not eliminate it. A top-heavy initial mass function would also mean more supernova feedback per unit stellar mass, more chemical enrichment, and different stellar evolution timescales, all of which would affect the interpretation of observations. Conversely, if the initial mass function is confirmed to be similar to the present day, it strengthens the case that the massive early galaxies are genuinely as massive as they appear, and the problem for theory is genuine. The initial mass function debate is part of a broader question about the universality of star formation. Is the process of turning gas into stars fundamentally the same everywhere and at all times, or does it vary with environment, metallicity, and cosmic epoch? The answer has profound implications for our understanding of galaxies, stars, and the universe. The tension with simulations. Why models fail numerical simulations are a key tool for understanding galaxy formation. Because the process involves complex physics, gravity, hydrodynamics, radiative cooling, star formation, feedback, chemical enrichment, that cannot be solved analytically, astronomers use computers to model the formation and evolution of galaxies in a cosmological context. Modern simulations, such as Illustris, Eagle, TNG, and Simba, follow the evolution of millions of dark matter particles and gas cells from the early universe to the present day, modeling the formation of galaxies within dark matter halos. These simulations include prescriptions for star formation, supernova feedback, black hole growth, AGN feedback, and other processes calibrated to reproduce observed properties of galaxies at low redshift. The simulations have been successful in matching many aspects of the galaxy population, including the luminosity and stellar mass functions, the sizes and morphologies of galaxies, the star formation rate, stellar mass relation, and the abundance of quenched galaxies. This success gives confidence that the physical processes included in the simulations are broadly correct. But when the simulations are run forward in time and their predictions for high redshift galaxies are examined, they do not match the James Webb observations. The simulations predict far fewer massive galaxies at redshift 10 to 13 than are observed. The most massive galaxies in the simulations at these redshifts have stellar masses of a few billion solar masses, not tens of billions. The bright end of the luminosity function is underpredicted by factors of several. Why do the simulations fail? There are several possibilities. One is that the subgrid models, the prescriptions for star formation and feedback that operate on scales smaller than the simulation resolution, are not accurate in the early universe. These prescriptions are calibrated to match low redshift observations and may not apply at high redshift. If star formation is more efficient or feedback is less effective in the early universe, the simulations would underpredict galaxy masses and luminosities. Another possibility is that the simulations lack the resolution to capture the relevant physics. Star formation occurs on scales of parsecs or smaller, far below the resolution of cosmological simulations, which typically have resolutions of hundreds of parsecs to kiloparsecs. Processes such as the formation of dense molecular clouds, the fragmentation of collapsing gas, and the interaction of supernova blast waves with the interstellar medium occur on small scales and must be modeled with simplified prescriptions. If these prescriptions miss important physics, the simulations will make incorrect predictions. A third possibility is that the cosmological initial conditions are wrong. The simulations start from initial conditions based on the lambda cold dark matter model, with a specific primordial power spectrum and cosmological parameters. If the actual initial conditions have more small-scale power, or if the cosmological parameters are different, the simulations would produce different results. A fourth possibility is that the simulations are missing entire physical processes. For example, magnetic fields, cosmic rays, and turbulence are often not included or are treated in simplified ways. These processes can affect gas dynamics, cooling, and star formation. If they are important in the early universe, their omission could lead to incorrect predictions. Addressing these possibilities requires developing new simulations with higher resolution, improved physics, and more sophisticated subgrid models. Several groups are working on this, running simulations specifically designed to study the high redshift universe. These simulations are computationally expensive, requiring millions of CPU hours on supercomputers, but they are necessary to test whether the discrepancy with observations can be resolved within the current framework. Early results from some of these new simulations show that by increasing star formation efficiency and reducing feedback strength at high redshift, it is possible to produce more massive galaxies earlier. But these changes are ad hoc adjustments rather than predictions from first principles, and they can conflict with other observations. The work is ongoing, and the final verdict is not yet in. The search for the progenitors and descendants, one way to understand the massive early galaxies is to trace their histories, identify their progenitors at even earlier times, and follow their descendants to later epochs. If we can observe a galaxy at multiple points in its evolution, we can directly measure how it grows, how its star formation rate changes, how its structure develops. This is challenging because individual galaxies cannot be tracked across cosmic time. The universe is too large, and galaxies move and merge. But statistical approaches can link populations of galaxies at different redshifts. By studying the properties of galaxies at redshift 13, 10, 6, and lower, and comparing their abundances, masses, and clustering, astronomers can infer evolutionary pathways. For example, the number density of galaxies with a given stellar mass can be tracked as a function of redshift. If the number density increases with time, it indicates that galaxies are growing in mass, either through star formation or mergers. If it decreases, it suggests that galaxies are merging together, reducing the number of individual systems while increasing their average mass. Preliminary studies suggest that the massive galaxies at redshift 10 to 13 are the progenitors of the most massive galaxies in the present-day universe, giant ellipticals and the central galaxies of galaxy clusters. This makes sense in the hierarchical model. The most massive halos at high redshift grow into the most massive halos at low redshift. But the puzzle is how they became so massive so early, far ahead of the schedule predicted by simulations. Another approach is to look for the progenitors of the massive early galaxies. Galaxies at even higher redshifts, redshift 15 or 20, that might represent earlier stages of their evolution. James Webb is beginning to probe these epochs, finding candidate galaxies at redshifts above 15. If these candidates are confirmed, and if they're found to be already massive or forming stars at very high rates, it would push the problem back even further, suggesting that galaxy formation began very early indeed. Conversely, if the candidates at redshift 15 and above are found to be small and low mass, as expected, it would indicate that the rapid growth occurred in a narrow redshift window between 15 and 10, a period of only 200 million years. Understanding what happened during this window would be key to solving the mystery. Tracing descendants is also informative. Do the massive galaxies at redshift 10 continue to grow steadily over time, or do they undergo bursts and quenching? Do they merge with other galaxies, or do they evolve in relative isolation? Do they remain star-forming, or do they become quenched and red? Observations of galaxies at intermediate redshifts, 6 to 8, can provide clues. Connecting progenitors and descendants is a major goal of observational cosmology, and the James Webb data are enabling this in unprecedented detail. The Cosmic Star Formation History. A revised curve, the cosmic star formation history, describes the total rate of star formation per unit volume of the universe as a function of cosmic time. It is one of the fundamental observables in cosmology, summarizing how quickly the universe has been converting gas into stars over its history. Before James Webb, the cosmic star formation history was thought to be reasonably well established. It rises from the earliest times, peaks at redshift 2 to 3, about 10 billion years ago, and then declines to the present day. This rise and fall pattern reflects the availability of gas. In the early universe, gas is abundant, fueling vigorous star formation. As cosmic time progresses, gas is consumed by star formation, expelled by feedback, or locked up in stars and remnants, and the star formation rate declines. The James Webb observations of massive early galaxies suggest that the cosmic star formation history at high redshift, above redshift 6, needs to be revised upward. If there are more massive, luminous galaxies than expected, and if those galaxies are forming stars at high rates, the total cosmic star formation rate must be higher than previously thought. Estimates based on the James Webb data suggest that the cosmic star formation rate at redshift 10 could be 2 to 5 times higher than previous measurements indicated. This has significant implications. A higher star formation rate means more stars are formed early, more heavy elements are produced early, more ionizing photons are released early, and more energy is injected into the intergalactic medium early. A revised cosmic star formation history also affects the total stellar mass density of the universe as a function of time. Integrating the star formation rate over time gives the cumulative stellar mass. If the star formation rate is higher at high redshift, the stellar mass density at intermediate redshifts will also be higher. This must be consistent with observations of galaxies at those redshifts, and it is. The observed stellar mass density at redshift 6 and below is consistent with the integrated star formation, given the new measurements. But the revised history also raises questions. If star formation was more vigorous at high redshift, where did the gas come from? Was the gas fraction of galaxies higher in the early universe? Observations suggest yes. High redshift galaxies have much higher gas fractions than low redshift galaxies, sometimes 50% or more of their baryonic mass. This abundant gas fueled the high star formation rates. But where did the gas come from originally? It accreted from the intergalactic medium, drawn in by the gravity of dark matter halos. The rate of gas accretion must have been very high enough to sustain the observed star formation rates. The cosmic star formation history is a key observable that connects the behavior of individual galaxies to the evolution of the universe as a whole. Revising it in light of the James Webb discoveries is an ongoing effort, with important implications for our understanding of how the universe has assembled its stellar content. Feedback's failure. Why didn't supernovae stop star formation? Supernova feedback is thought to be one of the most important processes regulating star formation in galaxies. When massive stars explode, they inject vast amounts of energy into the surrounding gas, heating it to millions of degrees and driving powerful winds that can expel gas from the galaxy. This reduces the gas supply available for star formation, potentially quenching star formation entirely in small galaxies. In simulations of galaxy formation, supernova feedback is crucial for preventing the overproduction of stars. Without it, simulations produce galaxies that are far too massive, with too many stars and too little gas, in contradiction to observations. Feedback is the thermostat that keeps star formation in check. But the massive early galaxies observed by James Webb suggest that feedback did not work as expected in the early universe. These galaxies have assembled enormous stellar masses, implying that star formation proceeded largely unimpeded. Why didn't supernova feedback stop it? One possibility is that the geometry of gas accretion matters. Gas accretes onto galaxies along cosmic filaments, narrow streams of matter funneling into the gravitational potential well of the dark matter halo. If these streams deliver gas directly to the central galaxy without passing through the outer halo, the gas is shielded from the effects of feedback occurring in the outer regions. The feedback energy is deposited in the halo gas, which expands and vents into intergalactic space, but the gas in the streams continues to flow inward, sustaining star formation despite the feedback. Another possibility is that the feedback energy is radiated away too quickly. For feedback to halt star formation, the energy must remain in the gas long enough to unbind it and expel it from the galaxy. If the gas is very dense, it can cool rapidly through radiation, converting the thermal energy injected by supernovae into emitted photons. The gas then recollapses under gravity, and star formation continues. In the dense environments of early galaxies, cooling times might be short enough that feedback is ineffective. A third possibility involves the timescale of star formation relative to feedback. If star formation occurs in short, intense bursts, a large number of stars can form before the first supernovae explode. By the time feedback starts, much of the gas has already been converted into stars, and the damage is done. Subsequent feedback might expel the remaining gas, quenching further star formation, but the galaxy has already accumulated significant stellar mass. A fourth possibility is that feedback is less efficient in more massive galaxies. The gravitational potential well is deeper, requiring more energy to unbind the gas. If the galaxy is massive enough, the escape velocity exceeds the typical velocities imparted by supernova-driven winds, and the gas remains bound. Only the most energetic outflows escape, while the bulk of the gas stays in the galaxy and continues to form stars. Each of these mechanisms could reduce the effectiveness of feedback, allowing more rapid star formation. But quantifying their importance and determining which dominates in the early universe requires detailed simulations and observations. This is an active area of research, with implications for understanding not only the massive early galaxies, but also galaxy formation in general. The role of active galactic nuclei, help or hindrance. Active galactic nuclei, supermassive black holes accreting gas and emitting enormous luminosities, are found in many massive early galaxies. Their presence raises the question, do they help or hinder the formation of these galaxies? On one hand, AGN can provide additional energy input, heating gas and driving winds even more powerful than those driven by supernovae. This AGN feedback can quench star formation, preventing galaxies from growing too large. In the present-day universe, AGN feedback is thought to be the primary mechanism that keeps the most massive galaxies from forming too many stars. On the other hand, AGN can also trigger star formation. The energy and momentum injected by an AGN can compress gas, increasing its density and triggering gravitational collapse. In some observed cases, regions of active star formation are found in proximity to AGN-driven outflows, suggesting that the AGN is inducing star formation rather than suppressing it. The net effect of AGN on galaxy growth depends on many factors: the luminosity of the AGN, the geometry and velocity of the outflows, the density and distribution of the gas, and the gravitational potential of the galaxy. In different contexts, AGN feedback can enhance star formation, suppress it, or have little effect. In a massive early galaxies, the role of AGN is unclear. Some of these galaxies show clear signs of AGN activity, with emission lines characteristic of ionization by a hard radiation field, and sometimes with broad lines indicating gas moving at high velocities near the black hole. Others show no signs of AGN, suggesting that their growth is driven purely by star formation. If AGN feedback is important in the early universe, it could help to explain why some galaxies are quenched. An AGN could heat or expel the gas supply, halting star formation and leaving the galaxy red and quiescent. But if AGN feedback is too strong, it could also prevent galaxies from becoming as massive as observed, worsening the discrepancy with theory. Alternatively, if AGN contributes significantly to the luminosity of these galaxies, the inferred stellar masses could be overestimated. Some of the light attributed to stars might actually come from the AGN. Disentangling the contributions of stars and AGN is challenging but necessary for accurate mass estimates. Spectroscopy is the key tool for this. Stellar populations and AGN have different spectral signatures. Stars produce a continuum of light with absorption lines from stellar atmospheres. AGN produce a continuum with strong emission lines from the ionized gas near the black hole. By carefully modeling the observed spectrum, astronomers can estimate the relative contributions of stars and AGN. Studies so far suggest that in most of the massive early galaxies, stars dominate the light, and AGN, if present, contribute a relatively small fraction. This supports the idea that the galaxies are genuinely massive in stars. But uncertainties remain, and ongoing spectroscopic surveys are refining these estimates. The heavy element puzzle: too much metal. Too soon. The metallicity of a galaxy's gas and stars reflects its history of star formation and chemical enrichment. In the early universe, gas is initially metal-free. As stars form, they synthesize heavy elements in their cores and release them into the interstellar medium through stellar winds and supernova explosions. Subsequent generations of stars form from this enriched gas, and the cycle continues. Observations of some massive early galaxies reveal surprisingly high metallicities, in some cases reaching or exceeding 10% of solar metallicity. This is far higher than expected for galaxies only a few 100 million years old. To understand why, consider the timescale for enrichment. A single generation of massive stars, with lifetimes of a few million years, can enrich the surrounding gas. But the yield of heavy elements per generation is limited. For a galaxy to reach 10% of solar metallicity, essentially all of its gas must be cycled through several generations of stars, with the heavy elements from each generation mixed thoroughly into the gas before the next generation forms. This requires not only time, but also efficient mixing. Heavy elements expelled by one star must spread throughout the galaxy, homogenizing with the remaining gas. Mixing is driven by turbulence, stellar winds, and supernova explosions, which stir the interstellar medium. But mixing is not instantaneous, and in large galaxies, it can take tens to hundreds of millions of years for enriched gas to be distributed uniformly. The observed high metallicities suggest that chemical evolution proceeded very rapidly in these galaxies. This is consistent with the high star formation rates and short timescale for assembling stellar mass, but it compounds the difficulty of explaining how so much happens so fast. Moreover, metallicity is not uniform within galaxies. Observations of nearby galaxies show metallicity gradients, with higher metallicity near the center and lower metallicity in the outskirts. This reflects the inside-out growth of galaxies, with star formation concentrated in the center at early times and gradually extending outward. If the massive early galaxies have similarly centralized star formation, their central regions could have high metallicity even if the galaxy as a whole is relatively young. Spectroscopy of high redshift galaxies typically samples the integrated light from the entire galaxy or from large regions within it. The observed metallicity is thus an average, weighted by the luminosity of different regions. If the central regions are metal-rich and bright, they dominate the spectrum, and the observed metallicity appears high. This could reconcile the observations with somewhat less extreme enrichment scenarios. But even accounting for spatial variations, the metallicities remain high compared to theoretical expectations. Models of chemical evolution in the early universe typically predict metallicities of 1% of solar or lower at redshift 10. Achieving 10% of solar requires invoking efficient star formation, efficient mixing, and possibly a top-heavy initial mass function that produces more heavy elements per unit stellar mass. The heavy element puzzle is another facet of the broader mystery. Everything about these galaxies suggests that they evolved far more quickly than we thought possible. The size-mass relation. Compact behemoth galaxies in the present-day universe follow a well-defined relationship between their stellar mass and their physical size. More massive galaxies are larger, but the relationship is not one-to-one. A galaxy 10 times more massive is typically only about 3 times larger in radius. This means that more massive galaxies have higher stellar densities. The size-mass relation reflects the balance between the processes that build up stellar mass and those that determine the distribution of that mass. Mergers, star formation, gas accretion, and feedback all influence galaxy sizes. Dry mergers of gas-free galaxies, tend to increase size without adding much stellar mass. Wet mergers, gas-rich mergers, trigger starbursts and can lead to compact configurations. Disk instabilities can funnel gas to the center, increasing central density. AGN feedback can puff up galaxies by injecting energy that causes stars to move on larger orbits. The massive early galaxies observed by James Webb appear to be more compact than galaxies of similar mass in the present-day universe. High-resolution imaging reveals that their stellar mass is concentrated in small regions, sometimes only a few hundred parsecs in radius. This makes them extraordinarily dense, with stellar densities exceeding those of present-day galaxies by factors of 10 or more. Compact galaxies at high redshift were known before James Webb. Hubble had discovered them at redshifts of 2 to 3, but the James Webb discoveries extend this to much earlier times and more extreme compactness. The reason for the compactness is not fully understood. One explanation is that galaxies form compact and then grow in size over time through mergers and other processes. Minor mergers, where a small galaxy merges with a larger one, can add stars to the outer regions without significantly increasing the central density, causing the galaxy to grow in size. Quenching of star formation in the center, combined with continued growth in the outskirts, can also increase size. Over billions of years, these processes transform compact, dense galaxies into the larger, more extended galaxies we see in the present-day universe. If this is correct, the compact, massive galaxies at redshift 10 are the ancestors of present-day ellipticals, observed at a time before they have undergone the size growth that will eventually disperse their stars over a larger volume. Another explanation is that the star formation in these galaxies is concentrated in the center, building up a dense core in a short time. Gas funneled to the center by gravitational torques or angular momentum loss forms stars rapidly, creating a compact stellar bulge. This is sometimes called inside-out growth. Over time, star formation might spread to larger radii, or the galaxy might accrete additional mass in its outskirts, increasing its size. A third possibility involves the role of dark matter. If the dark matter halo is compact, the gravitational potential well is deep and concentrated, causing stars to orbit on smaller, tighter trajectories. The stellar distribution reflects the potential, so a compact halo leads to a compact galaxy. But the size of dark matter halos is determined by the cosmological model and the halo's formation history, and compact halos are not typical. Special conditions would be needed to produce the degree of compactness observed. The size-mass relation at high redshift is an important diagnostic of galaxy formation processes. Comparing the sizes of galaxies as a function of redshift to predictions for models helps to constrain the mechanisms responsible for determining galaxy structure. Cosmic noon and its shadows. Connecting epochs. Cosmic noon refers to the epoch of peak cosmic star formation, around redshift 2, roughly 10 billion years ago. This is when the universe was forming stars most rapidly, assembling a large fraction of its total stellar mass. Galaxies at cosmic noon are well studied with Hubble, ground-based telescopes, and now James Webb. The galaxies discovered at redshift 10 to 13 in the first few hundred million years are observed at cosmic dawn, the very beginning of galaxy formation. Connecting cosmic dawn to cosmic noon, tracing the evolution of galaxies over the intervening 8 billion years, is one of the grand goals of observational cosmology. If the massive galaxies at redshift 10 are the progenitors of the massive galaxies at redshift 2, their evolutionary paths should be traceable. The stellar masses should increase as star formation continues. The sizes should grow as mergers add mass to the outer regions. The morphology should evolve from irregular or compact to more organized structures, spirals, ellipticals, or bulge-dominated systems. Observations at intermediate redshifts 6 to 8 provide snapshots along this evolutionary path. James Webb is observing galaxies at these redshifts in detail, measuring their masses, star formation rates, sizes, and morphologies. Comparing these properties to those of galaxies at redshift 10 and redshift 2 allows astronomers to piece together the narrative. Preliminary comparisons suggest that the massive galaxies at redshift 10 do indeed appear to be the ancestors of massive galaxies at lower redshifts. Their numbered densities, their clustering properties, and their stellar masses are consistent with this interpretation. But the timeline is tight. The growth rate required to connect a galaxy with 10 billion solar masses at redshift 10 to a galaxy with 100 billion solar masses at redshift 2 is very high, requiring sustained star formation rates or multiple major mergers. The shadows of cosmic dawn are long, reaching forward through time to shape the universe we see today. The massive early galaxies, if they're the seeds of today's giants, tell us that the foundations of cosmic structure were laid very early, and that the architecture of the universe was determined in its first moments. The frontier of theory. New physics or new astrophysics. The discovery of massive early galaxies by James Webb presents a fundamental choice for theorists. Is the solution to be found in new astrophysics or new physics? New astrophysics means revising our understanding of the processes that govern star formation, feedback, gas dynamics, and galaxy assembly within the existing cosmological framework. It means finding mechanisms within known physics that allow galaxies to form more rapidly and efficiently than current models predict. This might involve better modeling of turbulence, magnetic fields, cosmic ray pressure, non-equilibrium chemistry, or other processes that are difficult to capture in simulations. New physics means modifying the cosmological model itself, changing the properties of dark matter, dark energy, or gravity, or revising the initial conditions set by inflation. It means going beyond the lambda-cold dark matter framework to accommodate observations that it cannot explain. This is a more radical step with far-reaching consequences, but it may be necessary if astrophysical solutions prove insufficient. The preference in science is to exhaust astrophysical explanations before invoking new physics. This is a principle called Occam's razor, or parsimony. Do not multiply entities beyond necessity. If the observations can be